Questa era ancora di Riccardo. Eccoci.
So please take a seat, we can start.
We start with Sergio Greco with the session focus on work package 9.4. Please, Sergio.
Okay, thank you, and welcome to the first section of the day. This is about the the work package number 4. On the slide, you see the key person, the key people: Sergio Flesca, Filippo Purparo, Cristian Molinaro, Andrea Tagarelli, and the co-PI Irina Trubizzina. So, the work package is about explanations in artificial intelligence, and we have 3 main research lines: abstract argumentation, explanations, and the graph neural networks and the social media. The first task is about the use of argumentation for explaining sequence of events and to detect deviation from desired behaviors. In the first phase of the project, we have designed one architecture to explain sequence of events, and this is the architecture you see in the top side of the figure. Now we have extended this architecture by adding 1 second module, which is based on the machine learning paradigm. And this is, in the previous architecture, an important role was the role of the domain expert. And now this module is useful to reduce the role of the domain expert, or to replace the domain expert. In the second task, we are concentrating on extensions and explanations of abstract argumentation. In the first phase, we have concentrated on extensions of abstract argumentation, and we have proposed several frameworks which combine abstract argumentations with other formalism, such as constraints, preferences, incompleteness, probabilistic reasoning. We are now working on explanations, and we have proposed a new framework which is extends argumentation, abstract argumentation, by providing explanations for extensions for models. In this task, there are also important contribution of our partners, which are the University of Brescia and the University of Chieti Pescara. And next, there will be 2 talks which refer on the recent results they have obtained. The third line is about explanations. We have investigated 2 lines here. One regards the global explanation, and the second one, the local explanation. The next talk of Gianvincenzo Alfano will be about local explanations. But there is another important research line which refers to global explanations. In this case, the research has concentrated on the identification of necessary reason to detect and to identify explanations, or to identify a set of objects which belong to the classes. This is important in classification to model and to describe the characteristic of the models. The fourth research line regards graph neural networks. In particular, we have concentrated on link prediction in the multi-layer network graphs. Here we have proposed an architecture which is to predict links among nodes, which is based on the ensemble paradigm. And in particular, we have several predictors which are showed in the right part of the figure, and each predictor has associated a weight which is established on the base of some heuristics. And at the end, the prediction is done by considering the weighted predictors. So here there is a weighted voting mechanism. And the last line of research is concentrated on social media, which is connected to, of course, to graph neural networks, and in particular on the identification of polarized groups. Here we have proposed an algorithm. This is a very complex problem, because this is a problem similar to the identification of clicks in graphs, and we have proposed a greedy approximation algorithm, which from the experiments seems to be good from the point of view of the approximation, but also from the computational point of view. Okay, just a few words on the publications. We have published several papers in A-star conferences and several papers in the Q1 journal. Most of them are published in a conference journal which are in the area of artificial intelligence, of course. Okay, that's all. Thank you. And now I would like to invite the first speaker, which is Gianvincenzo Alfano.
Okay. Good morning, everyone. I'm Gianvincenzo Alfano, and I'm going to talk about even-if explanation, formal foundation, priorities, and complexity. As you can see, this is a joint work with Sergio Greco, Domenico Mandaglio, Francesco Parisi, Reza, and Irina. This work has been recently accepted at III 2025. And in our work package, recently we post our attention to explanation method in AI fields. I start with an introduction on explainable AI. So as Sergio this morning said, there are two main paradigms to explain black box models in machine learning. The first one is the global explanation that aim to explain how the black box operates independently of the specific input. The other approach is the so-called local explanation, in which we aim to explain the outcome of a specific input. And this is our focus, and particularly on local post hoc explanation. So post hoc means that we assume the model is a black box, has been already trained. Okay, so machine learning models often operate as black box, lacking explainability and transparency, while supporting decision-making green-aware processes. Okay, so what has been done in literature so far is to propose two approaches. One is called factual explanation, that reveals only the why an input has been classified in a certain way. And it cannot be sufficient to understand how to change the outcome. The other approach that received lots of attention is the so-called counterfactual explanation that suggests what should be different in the input distance to change the outcome of an AI system. To make an example, assume to have a machine learning model classifying products as either eco-friendly or non-eco-friendly, based on various features like carbon footprint, recyclability, material sourcing, and so on. So a counterfactual explanation of why specific input has been classified in a certain way corresponds to the if-only thinking. So if only the product's packaging had been made from 30% more recycled material, then the model would have classified it as eco-friendly instead of non-eco-friendly. So we start typically in a situation that is negative, and we would like to have to find the minimal changes to flip the decision outcome. Okay, so however, limited focus on the equally important semi-factual explanation have been posed so far. So we proposed the concept of even if explanation, also called semi-factual explanation. So an example of semi-factual explanation could be the following. So even if the product's packaging had been made from 30% less recycled material, then the model would have still classified it as eco-friendly. So in a sense, we start with a positive situation, and we would like to find the maximal changes that preserves the classification. Okay, so to make another example on images, suppose that we have a test image, a test image, and we would like to explain the factual reasoning. So a factual explanation simply says why the test image is a 9. The counterfactual explains what minimal change are needed to classify the test image as not a 9, and the semi-factual corresponds to what maximal change ensure classifying the test image as 9. Okay, of course, the number of counterfactual and semi-factual explanation for each specific input could be exponential in number. About the contribution. So we show that both linear and tree-based model are strictly more interpretable than neural network under semi-factual reasoning. I will discuss on this what it means. We introduce a preference-based framework that enables the user to personalize explanation based on their preferences. Recall that they are exponential in number, so we would like to prefer some of them based on user preferences. And we also explore the complexity of several interpretability problems in the proposed preference-based framework and provide algorithms for the case that we show that they are polynomially computable. Okay, so what kind of classification models we focused on? So we focus on binary classification model, and particularly on 3 well-known classes. Multi-layer perceptor, so in a sense they are feed-forward neural network with ReLU activation function in intermediate layers, and the step function at the last activation function. Also the perceptron, that is a special case with no hidden layer. Intuitively, it could represent a support vector machine. And also the free binary decision diagram, that is binary decision diagram where for every path from the root to a leaf, no 2 nodes on the path have the same label. Okay, so in a sense, the first model is a nonlinear model, the second and the third are linear and tree-based. Okay, supposed to have a perceptron that is a classification model, a binary classification model that represents a mortgage scenario. So what is the input here? Are user with 3 features, F1, corresponding to part-time employment contract, F2, mortgage term longer than 30 years, and F3, on-site working. In this cube, the crosses, the green crosses represent instances, so user, where the model outputs 1, and the circles in red represent instances where the model outputs 0, so the loan is rejected. Suppose we have user x1, 0, 1, 1, that works full-time, okay, because f1 is 0, on-site, because f2 is 1, and request a mortgage with a duration longer than 30 years. And the loan has been accepted. So it's a user where the bank, using this model, says, I give you the loan, okay? Good. So this is the definition of counterfactual explanation that has been proposed by Pablo Barcelo and others. Given a pre-trained model M and an instance X that in our example is a user, an instance Y is said to be a counterfactual of X if and only if the model changes the output, okay, and Y is at minimum distance from X. So there exists no other instance Z that flips the output and it's at a distance lower than the one of Y. So in this case, to have an example, for the user x1, the only counterfactual explanation is y3, according to this definition, that is at distance 2. Observe that 1, 0, 0 is not a counterfactual at minimum distance because the distance is 3. Okay, so in this case, the only counterfactual explanation is 1, 0, 1. Okay. Okay, what we propose is the definition of semifactual explanation, in which, given a pre-trained model M and an instance X, an instance Y is said to be a semifactual if the model preserves the classification, and Y is at maximum distance now, okay? Let's give an example. So, for X1, we have two semifactual explanations that are y1 at distance 2 and y2 at distance 2. Okay? What does it mean? For example, y1 is an explanation of this form. Even if the work would have been remote and the mortgage duration would have been less than 30 years, then the user will obtain the mortgage. So, in a sense, this represents degree of freedom. So imagine the user wants to apply for a loan, okay, and the loan is accepted. So a semifactual could give the user the possibility to apply again with less restrictive constraints, okay? This is just to give the hint. Okay, so what we did is to formalize this problem. The problem maximum change allowed is a decision problem, and is the natural decision problem related to the optimization problem of finding counterfactuals. And it outputs yes, so given a model and an instance X and an integer K, we output yes if there exists an instance Y with a distance greater than K that keeps the classification, no otherwise. So this problem, we show that this problem can be computed in p time, polynomial time, for free binary decision diagrams and perceptron, and it's NP complete for multi-layer perceptron, so for feed-forward neural network. So the take-home message 1 is that independently of the type of the model, computing semifactual is as hard as computing counterfactual. The result for counterfactual has been showed in the paper I mentioned you before, the NeoRIPS paper from Pablo Barcelo. And they also have the similar result for counterfactual reasoning. Okay, the second take-home message is that the linear model are strictly more interpretable than neural network. So in the sense that the complexity of answering these explainability queries for models in the first two classes is lower than those in the latter. Okay, so this is the first contribution. Let's move now to the second contribution related to preferences. Recall that the number of counterfactual explanation and semifactual explanation are potentially exponential. And we would like to have a way to the user to express preferences over this explanation so that the best ones are eventually selected. So we introduced a novel approach inspired to the answer set optimization approach, well-known approach in answer set program proposed by Gerd Brefka. In our approach we have preference rules. I will explain in a while. What does it mean? So preference rules determine a preference ordering on explanation so that the best ones are selected. So we can model binary classification model with preferences, in which we have a black box model and a set of preference rules of this form. What does it mean, this preferences K? So the user prefers explanation where? So if we have two explanations, both where the work is not on site, so where not F3 holds, the user prefers explanation where the contract is part-time, so F1 holds, and if this is not possible, the user then prefers those explanations where the mortgage duration is not longer than 30 years, so when not F2 holds. Okay, so the preferences apply is a conditional preferences and applies when the body is satisfied. Okay, so what we did is to also focus on a restricted version of this model called linear, where we have a single preferences rule with empty body. This could also model a sort of ranking among the feature. Partial or total. We investigate also the decision problem, analogous to the maximum change allowed I showed you before, in case of linear preferences. So in which we do not only have the model, so we do not only want to explain the output, but we would like to explain and also apply preferences. So in the first row, I reported the result I mentioned you before on counterfactual explanation. And if you see the first row, this corresponds to what I said you before, that independently of the kind of model, the complexity of computing counterfactual and semifactual is the same. Then, in the last row, we also investigate the problems in which we have counterfactuals and linear preferences and semifactual and linear preferences. And here the take-home message is that linear preferences do not increase the complexity of computing, the best semifactual or the best counterfactual. In the case of perceptron and FBDD, so for linear model, through they allow expressing user-specific desiderata among queries. So we have the same complexity, but we are more, we allow to express some user desiderata, like preferences, okay? Okay, so when, for the two case when we showed the p-time complexity, so for perceptron and a tree-based model, we provided algorithms for computing the best semifactual and counterfactual explanation, okay? In the paper, you can also find the ways of computing best counterfactual also. So we also provide the algorithms for the best counterfactual. Okay, I come to the conclusion. So in this work package, we also investigated semifactual and counterfactual reasoning and argumentation. That is the topic on the task 9.4.2, and also 9.4.3 related to explanation. So as future work, we would like to explore additional interpretability queries, for example, by quantifying the number of explanation, and also dealing with real number inputs and non-binary discrete feature. We chose that one because we put our setting in the same way Pablo Barcelo did in his paper, just to compare with the counterfactual reasoning. And as last future work, we are actually investigating interpretability queries for other class of machine learning model, like graph neural network, also interrelated with the work package 9.4, and specifically the task 9.4. Okay, thank you. I would like also to thank the co-author. Thank you.
Thank you. Any question? Pasquale? Okay. How do you prefer?
Okay, thank you for the question. In our setting, we assume the model is fixed and pre-trained, and we assume it to be a black box. So any techniques that converts nonlinear to linear models could be used as a pre-processing step, and then we could explain the output of the obtained model. What is interesting, and actually I don't know the answer, is whether if we assume that for each specific input we have the same output, okay, this approach will work. But if the obtained model is an approximation of the initial model and we have a different result, of course the explanation on the second model could be different to the ones obtained on the first model. So it depends on how precise is the transformation approach. Thank you for the question.
Other questions? Okay. Yeah, it's better to use the microphone.
How many even if you have tested?
What do you mean?
There are even if semi-factual, even if clauses are there. So how many even if you have tested for the model?
Okay, this work is mainly theoretical. Okay, so what we did is to propose the definition of semi-factual explanation. Then we investigate the complexity of the associated problems. Okay, and we didn't investigate in practice. There are also works that that explains that explains practically. Okay. But this work is mainly theoretical. I don't know if this was the question. Do you want to add something?
In the even if you have one condition, a logical condition.
Yes.
So you can compact in only one even if, no? Making one complex logical formula.
I think there is one matrix confusability in case of even if, because it creates confusion sometimes. When you talk about the even if conditions, clauses.
Of course,
So
depends on the logical formula.
Yes,
on
that's
the logical,
why.
yes, depends on the logical formula.
Yes, yes. So
If we have one conjunctive logical formula, I don't think there is confusion. But if you use more disjunction or other, you complicate the logical formula, this could happen.
Anyway, excellent.
Thank you.
I have a question.
Oh, okay.
Even if I have, I am the co-author. In the last slide, you mentioned that the technique can be extended for other neural network formalism. But can be used for standard classical machine learning techniques. For instance, in nearest neighbors, this could be used to, when you assign the class, you do prediction, this could be used for, to improve the quality, to check, don't only to check in the neighborhood the number of...
To approximate the decision boundary, you mean?
Yes, but to say that, to give one, you can say, that if the counterfactual, is
far or not? Okay.
Yes.
It gives also
considering
okay.
How far is the counterfactual, but even the semifactual, you can say, you can be more confident when you assign it.
Yeah, you're right. You're right. Absolutely. Yeah, this should be also investigated because the counterfactual gives you the minimal changes. So in a sense, it gives you an hint to how far is the next point that has been classified differently. And in the same way, the semifactual is giving you a hint on what is the farthest point in your cluster. So in a sense, you are approximating the space of point that have been classified in the same way. But in this kind of works, typically they consider these three models, and also there are works on counterfactual explanation in graph neural networks. But on this, I never thought about this approach in classical machine.
You mentioned in the beginning that in the decision tree, the same label is not used at the time.
Not in the decision, in the free binary decision diagram.
In the free binary,
it's a special class.
Yeah, it's a special class.
Yeah.
But if the features are binary,
okay,
you never use the same label to more than
you use the same label to decide the path. Okay,
yeah,
it's redundant.
If the
it could be redundant.
If you consider binary features, you never can use more than once the same feature.
Why not? You mean so if you are already in the path in which it's just redundant. I agree with you. They assume this just to make it shorter.
It's intrinsic in the fact that you have a binary.
Just going ahead.
Okay, we are right. Okay, thank you. And
thank you.
Let's pass to the second presentation of the section. What is the order? This?
This.
Okay, the new one.
Okay, may I?
Yes.
Okay, good morning everyone. So this is a talk from University of Chieti Pescara. The title is Strategic Reasoning with the TSLA, which is an acronym for Timed Concurrent Language for Argumentation. Our team in Pescara is made of 4 people, apart from myself and Francesca, who are both here. There is Maria Chiara Meo and Fabio Fioravanti. And actually, this talk of today, the author of this is about a paper whose author is Maria Chiara Meo, and she was supposed to be here, but at the end she couldn't. So I'm going to present it, although I was not directly involved in this work. And this is a joint work with Stefano Bistarelli and Carlo Taticchi from the University of Perugia, which often collaborates with us on these topics. So since this is a quite heterogeneous audience, I also think to give an introduction to abstract argumentation, which is the broad topic of this talk. Then I will introduce this language, this time concurrent language for argumentation. And at the end, we will show how this language can be used for strategic reasoning. Okay, so what is abstract argumentation? First of all, what is argumentation? There are many different definitions of argumentation. Let's say that it's a kind of communication activity between agents in which these agents exchange arguments, reasons, and try to support these arguments or to challenge these arguments. In computer science, often there is a core concept in argumentation, which is that of argumentation framework, which is kind of abstractions of the arguments and the way these arguments attack themselves. What is an argumentation framework is a graph, like a directed graph, like the one you find on the right of the slide, in which the nodes are the arguments, are the positions of the agents, and arrows are attack relations. Everything is very abstract. There is no internal structure in the nodes, but you may think that each of these nodes is kind of a real argument in, I don't know, like in natural language. For example, you can think that A is the John killed the victim. If you think there is a kind of murder, something has been murdered, and so the position A, the argument A, is that John killed the victim. But then someone says that at the argument B, which is that there is no evidence that John killed the victim, and so the argument B attacks the argument A, says, no, that's not true. And then someone says, oh, but the doorman has seen John at the scene of the crime, and so the argument C attacks B. It's not true that there is no evidence. There is. And finally, another argument D comes out, which says, no, it's not possible that John was at the crime scene because it was seen at class teaching at many students. And so D and C attacks each other because only one of them can be true. Okay. So, once we have an argumentation framework, it's not possible to, let's say, believe or accept all arguments because they contradict each other. There are several, let's say, things called argumentation semantics, which establishes which subset of arguments are acceptable. The simplest of these semantics is the conflict-free semantics, in which we establish that we can accept subset of arguments, every subset of arguments, which is not self-contradictory, in which arguments do not attack each other. So, for example, the set, the singleton A, is acceptable with respect to this conflict-free semantics because A does not attack itself. And the same AC is acceptable because they don't, A and C don't attack themselves. And BD is acceptable. But the pair, the set AB is not acceptable because it's self-contradictory. This is a very simple semantics, which actually too simple to be of real use. So generally the semantics which are used are more complex. Let's say that an immediate step further is that of admissible semantics. In the admissible semantics, we accept a subset of arguments which are conflict-free. But we also require this set of arguments to defend themselves from others. If someone else attacks the set S, then S should counterattack. Let's say that A was conflict-free, but is not admissible because A is attacked by B and by D, and A does not nothing to protect himself, does not try to say, okay, B, you're wrong. While AC is admissible, because although, for example, B attacks A, The argument C defends A by attacking B, okay? So it's C defends A from the attack of B. And also BD is admissible, okay? So there are different admissible sets of arguments. The set of acceptable sets for a given semantics is called the extensions, are the extensions of an argumentation framework. And finally, let's say this is the last topic for this introduction on argumentation. Sometimes we want to use argumentation framework like an inference tool. There are generally two ways in which we can use argumentation framework as an inference tool, a skeptic and a credulous way. Given an argumentation framework, a semantics, sigma, and an argument A, we say that this argument A is accepted skeptically when it appears in all the extensions of the argumentation framework, so in all possible acceptable set of arguments, while we credulously accept the argument A if there is at least one extension that contains A. So, for example, on the right you find two acceptable, two extensions for the acceptable semantics, the two that we have seen before, and since A appear in one of them, then A is accepted, is an accepted argument under the credulous semantics. While A is not accepted with the skeptical semantics because A does not appear in all extensions, just in some of them. Okay, so these argumentation frameworks so encodes arguments and their relation, but lacks dynamic. Okay, we say that the argumentation is a sort of dialogue between parties, and there is no dynamic here. It's a kind of frozen state of affair. There are several ways that can be used to provide dynamics to this to argumentation frameworks. The one we propose is this language called timed concurrent language for argumentation. What is this language? It's some way similar to TCCP, which is timed concurrent constraint programming. Let's say that it's a language in which there are agents, concurrent agents, there is non-determinism, and these agents communicate among them using a common store. But instead this common store to be just a set of variables or constraints like in other formalism, the common store is an argumentation framework. And so the language, the agents can interact with this common argumentation framework by, I don't know, joining attacks, removing arguments, or querying the argumentation framework. This is the syntax of the language. The A in particular is the syntax category for agents. So an agent can be either a successful or a failed agent. An agent can add an argument and a set of attacks to the argumentation framework before proceedings, or it can remove attacks and arguments before proceedings to another, to a smaller agent A. This is the parallel composition of two agents. This new S in A is a way of hiding, let's say that inside A, the set S is a set of arguments. Those arguments become private to A, so they are not visible from other agents. And this is a quite recent addition to this language, which is used to model the idea that some agents have some private information don't want to disclose. And then there is a call to a procedure call, okay? There is a set of procedure definition, which is C, and in this way we call one of these procedures. Okay, I skipped here one of the definition of agents. I'll be back later to that. The behavior of this language is described by a small step operational semantics, a la Plotkin. States are tuples, AFT, where A is the current agent, F is the current argumentative framework, and T is called timeout environment and is used to keep track of time, but we'll see it later. And so just an example of a very simple rule, which actually is simplified with respect to the real one, is the following. If we have an agent of this kind, so that on this argumentative framework and on this timeout, the state transition in a new argumentative framework where we have adjoined the arguments in arg prime and the attacks in r prime to the original one. And now the current agent is just the piece A. Okay, but actually the most interesting part of the language is this kind of agents, which I highlighted now, which are the guarded agents. What are guarded agents? It's essentially a non-deterministic choice. Okay, so you have a plus here, which represents a non-deterministic choice between agents prefixed by a guard. A guard is a condition that we need to check in the argumentation framework, and only if the check is satisfied, we can proceed with the execution of the agent. And there are three different checks. A syntactic one that is... What happened? A syntactic one will only check if a given argument or given attacks are in the argumentation framework. So if there is no semantic check here. And a pair of semantic checks, C-test and S-test, which actually query the argumentation framework and asks if a given argument A in a given semantic sigma is accepted or not accepted under either the credulous or the skeptical semantics, which are the things we have seen before. So when an agent of this kind is executed, the abstract argumentation framework, the current argumentation framework is checked. If the argument A is can be accepted with the credulous semantics, we proceed further. Otherwise, the agent is stuck there. But it's not stuck there forever. It's stuck there only for a given number of time steps t, and when these time steps pass and the guard is not satisfied, the agent fails, goes in the failed state. And okay, the last part of the states in the operational semantics, the timeout environment, is essentially used to keep track of the current time. Essentially, it's a map, it's a function from an agent to the current timeout of that agent, how many time steps can pass before that agent fails. Okay, and at each time step, all these timeouts are decreased. When one timeout reaches 0, the corresponding agent fails automatically. This language has been, actually, there is a prototype of this language, which is online. It's nice to play with it. It's not particularly fast, but it works. Okay, last part is strategic reasoning with this language. There are, in the literature, several ways, I say, to give dynamics to model some kind of argumentation. For example, one of these is the symmetric strategic argumentation dialogues. It's a game between two parties in which there is a common topic, and one of the two parties, the proponent, wants to defend this argument, while the opponents, try to refute this argument. This argument is called the topic of the dialogue. And the two parties take turn proposing new arguments which attack or defend the topic. The point is that the two parties does not want to reveal immediately all the arguments they have, because I know there is some arguments they want to keep secret if it is possible, okay? And so they start from an empty situation, an empty argumentative framework, and when they are forced, they try to add a new argument to back up or to refute the topic. Like, for example, a dialogue between a police officer and a people with suspected of the crime, like before, in which the topic is you killed the victim, and then the opponent says, which is the person which is accused, says, no, it was not me, there is no evidence, and then the police officer says, but no, we found your ID card near the scene. And the other defend himself. Oh, okay, my ID card was stolen, so it does not prove nothing. And then the police officers try a different route, say, okay, but your car also was seen near the scene of the crime. And okay, and so on. I mean, we can proceed until one of the two parties, agents, don't have a counter argument. Okay, I will skip this part because it's, I think we're already a bit late. Let's say that the dynamic involved in this process, in this dialogue, can be encoded by a program, an agent in this language, which faithfully represents the dialogue. And it says that the execution of the agent terminates, and if at the end, the final argumentation framework, if in the final argumentation framework we have a loser Pierre fact argument, it means that the proponent loses. If the final argumentation framework have a loser op fact argument, it means that the player opponent loses. And like this, there are possible to model, and we try to model different kind of dialogues and games, with different definition and different points of view, like this multi-agent decision making with privacy preserved. Okay, so future work, we try to model, want to model multi-policy system selection and composition using this language. The idea is to model problems in which there are, for example, want to make some trade-off between performance and energy consumption. And so we have different stakeholders who want to push for more performance or for lesser energy consumption. We want to enhance the prototype, which at the moment is not very fast, and we think to enhance the prototype by integrating with existing argumentation libraries or frameworks like SPIC+, and introduce some constructs that simplify translations like this one, which at the moment are quite complex and generate very long programs. And that's all. Thanks for your attention.
Thank you. Questions? Okay, just one short question. I didn't. You describe how the framework is built, no, by agents which operate concurrently. But I didn't see. Maybe I have lost something. I didn't see something to check. If one player is the winner, why he has to modify? He doesn't modify. So before deciding to do something, he has to check the status of the.
Oh yes, but you see
maybe I have lost something.
There are these guards, these guarded agents here, that check the current state of the argumentation framework. So, for example, in the modelization of the previous problem, which there is the proponent and the opponent, we try to defend a topic. Essentially, both of them becomes an agent in this language with a, let's say, a loop in which they check the argumentation framework, and when they see that they are losing because the topic is not acceptable or it is acceptable, they can move and make and add something to the argumentation framework. But the way they can check is through guarded agents, so agents that stops until some events does not occurs in the argumentation framework.
Okay, thank you.
You're welcome.
Okay, thanks. So the next speaker should be Cerutti, Federico. I don't know if it's online.
Hello, Sergio. Can you hear me?
Hi, Federico.
Hi, Federico.
Okay, yeah.
Okay, yeah.
You hear?
You hear?
Yep. We hear you.
You hear?
Are the slides showing or?
Yeah, for
us it's fine, I think.
Francesco,
Can I begin?
You can start.
You can start. Yeah, you can start.
Thank you very much. Good morning, everyone. Thanks for having us remotely. And this is presentation about the Cascade core that we are leading at the University of Brescia, and this is a joint work with Pietro Baroni, Massimiliano Giacomin, Gianfranco Lamperti, and Marina Zanella. So let me start by mentioning motivation on where we start from. So this graph shows us at the bottom part here that the joule for FLOP, or floating point operation, is decreasing across time, but then, especially after the 2012, with the increase in use of deep neural network, in particular for image processing at the beginning and now natural language processing, the total amount of energy that we are using for AI consumption for generation of models is rapidly increasing, with the corresponding increase in the total amount of CO2 that we are emitting in the atmosphere. So this is just, according to some economists, just another manifestation of the Jefferson paradox. So in the long term, an increase in efficiency in resource use will generate an increase in resource consumption rather than a decrease. And we are experiencing something very similar nowadays. So what we are trying to do in this Cascade core? Well, we are trying to look within this widespread application of deep neural network, in particular nowadays for natural language processing and the use of parallel GPU clusters, with the idea to identify and investigate causal relationship related to energy consumption and design intervention to reduce energy use. So in particular, we are taking a human-centric and ethically aligned approach. This requires us that we should ground our decisions into some formulas that a human can review and interpret. We want to acquire situational understanding of energy consumption. We want to have a causal description of this behavior, and very similar to what Gianvincenzo was describing before, we actually want to have at least some level of intervention on this type of representation. So that's why we want to have the ability to identify strategies to reduce energy consumption and waste. So because of our first objective, so everything should be transparent for an ultimate human decision maker, we are grounding our investigation in argumentation-based systems, although not as formal as what Gianluca was presenting, but I'm coming to that in a second. So argumentation is clearly a fundamental component for causal discovery, and that is because you probably heard several times correlation is not causation, yes, And indeed, if you read the literature, including, for instance, the chapter of the handbook of argumentation that we wrote as part of this cascade call, then you will see that there are several instances of several types of arguments that are being proposed in the literature for arguing against or in favor of causal links. So in this way, argumentation can give us the ability to foster a balanced and comprehensive view through a nuanced discussion on whether two variables should be one the cause of the other. In the scenarios with scarce data, and this is one of those because collecting data about the consumption of deep neural network is not easy. I'm coming to that in a second. And also it's very difficult to have a comprehensive coverage of all the possible hyperparameters, architectural choices, any little variations for getting a very full view, data-driven. And also because we want to engage in informed discussion with human decision makers. Now, at the same time, we don't want to ignore that there are decades of research in argumentation. In particular, we are also grounding our research in GDS structural causal models. So this is using structural equation and direct graphs to describe deterministic functions linking cause and effects, where the uncertainty is associated with stochastic noise. And those models can be used to model both direct and indirect causal relations. And they support also different level of reasoning, from associational, so what are we actually observing, so sort of conditional probabilities, interventional, so on a statistical level, what would be the impact if over the population we would change some variable, and that is the G operator. And also counterfactual, especially if you have computed those functions, which is very similar to what Gianvincenzo was describing before. So for a specific decision, I think he was referring to some local explanation in his talk. So for a specific decision, then you want to just change some of the features. So for instance, in this research, we're probably going to focus more on the conventional because we are reasoning over distributions of variables. So we might see that the batch size might cause GPU memory to increase, which might increase the power consumption. So we can answer queries like what would happen over the population of all the possible training of this type of neural network if we will reduce the batch size. However, what's the problem behind this GDS model? Is brilliant if you want to use it for reasoning, for counterfactual reasoning, for do operator, but it tells you very little about how you can create those links. So GDS framework starts with a direct acyclic graph that represents the causal relationship between variables. But we want to create this graph as well. Now, what are the fundamental elements for arguing about the causal links? We need observations, we need causal explanation, but we also need conceptual knowledge. So without just data-driven will not be enough, so observation will not be sufficient, otherwise there will be a very easy problem. We want to derive causal explanation, and that opens up the question to which type of meaning of causality we have, ceteris paribus, necessary, sufficient conditions. So all of those are different, tiny view of the same broad concept of causality. And overall, we actually need to be able to argue in favor and against those causal links, and so to be open to possible critiques about these associations in the same way we would do in a scientific discussion. So just to quickly mention, but as I said in the chapter, there are more details of this survey. There are several arguments in favor of causal links, from circumstantial evidence to contrastive evidence like B of course under A but not under not A, to causal explanation where we actually have a mechanicistic approach, description of what is linking a cause to an effect. And clearly we also have arguments against causal links. So we might have closely challenges. Maybe the temporal order is wrong. maybe the cause is neither necessary nor sufficient. Or logical challenges like there are other explanations, or you are putting forward a fallacy like a post hoc ergo propter hoc. So this, in the idea of argumentation theory, should be seen as sort of critical questions putting forward against a causal link proposal, which can also ended up strengthening the actual proposal, because standard argumentation theory, but also standard scientific process, if you are criticizing your hypothesis and your hypothesis stands against all the critics, then it's actually strengthened at the end of the discussion. So what we did so far, and this is actually going into the direction of current and future work. So first we tried to think, collect data sets ourselves about this energy consumption. We have a few clusters here of GPUs. But the complexity of controlling all of those experiences, plus requiring complete access to the machine and therefore blocking a few dozen of students from doing their own research was a cost too high. But also there was another aspect. There is already a very good data set out there, and it's coming from the National Renewable Energies Laboratory of the United States of America. It is collected from 63,000 experiments with 30,000 configuration. It considers 20 model sites, different, all of them are neural networks, different network shapes at the same time, different depths. And also they were collecting watt meters, both of the CPU and the GPU. And honestly, it's already out there since a few years. It's been already cited by several other researchers. So we decided to go with this data set. Now the data set was not exactly designed for what we wanted. In particular, there were slightly different view of what it was meant to see. But essentially what we had to do is to join a few tables to bring together the result that we actually expected from this data set. So in particular, we wanted to just filter out a lot of the information that were there from the data set and focus more on the execution metadata, so the parameters, the models, and with the actual energy matrix that was coming out, and just consider the total energy, not just distinguishing between CPU and GPU. But in any case, the problem here was becoming a sort of a regression problem. So given this set of parameters, how much would cost us training this more intense watt usage? So instead of approaching this one as a black box, we wanted to use causality reasoning. So we started to use the very simplest structural learning algorithm, which is the PC algorithm. And this is very data driven. So let's suppose that we have on the left the ground truth. This is the causal model generates a data set. So the data set is a big table with these 4 variables, and this is the causal model that is behind, and we use the function that links them with the stochastic noise, etc. So what the PC algorithm does, it starts with a fully connected graph among all the variables. Then it starts looking at couples to see whether there are conditions, whether they are independent unconditionally. Now, if we are just restricting between the columns that links y and x and y, then these two variables will result as unconditionally independent. We use the Fisher test for this one. So we can remove this edge, because x and y will not be connected. We can also do the same conditionally independently. So if we condition over z, then x and w and y and w also become independent, meaning that is z that is inducing some level of dependencies between them. Now this is creating a B structure. It is a standard procedure in elimination in GDSPR theory, so we can just detect which one is could be the arrow, the direction of the arrow, and then in similar way we can actually detect. Now, this is clearly a toy example just to explain the algorithm. In the real world, these things become more messy. So this is actually the analysis that we did from the data set that we were using. Some things are relatively reasonable, like the shape might impact the depth. But then we might have that the power is affecting the size of the power used is actually affecting the shape, which clearly seems to be a wrong connection here. And here is what we are working on right now. So instead of throwing away everything or starting from scratch with some new idea, what if we can use argumentation to refine what we already found out? So we start from a very simple algorithm like PC, but we can use FCI and any other type of algorithm, that's no problem. Then, from the structural learning, from the structure that we learned, we use, and in this case, and I will comment on this bit at the very end, we are going to use large language models to argue in favor and against those causal links, with some caveats. So in particular, we are planning to use few-shot learning or setting, depending on the terminology you prefer. So we want the LLMs to reuse the type of arguments I described in before, in terms of, okay, we want to have arguments from sufficient causes, or we want to have argumentation structure that are describing the actual process behind the cause and effects. But also, we want to have the counter-arguments, and the counter-arguments can follow the structure I mentioned before. So, by merging these aspects together with a formal mechanism, which could be very similar to what Gianluca described before in terms of a dialogue system that one LLM put forward an argument in favor of a causal link, another LLM is putting forward a counter-argument, and clearly put down something in the prompt that says, okay, if you don't have any more counter-arguments, you should stop. You can have some level of preferences also, which could help us describing which counter-argument might be stronger than others. But the idea is that these could provide us a principal fusion of empirical structural learning, like the program counter, the CC algorithm, and natural language augmentation to support causal inference on uncertainty. So let me give you just a couple of examples. A causal link that was coming out before was the neural network is affecting the batch size. And this is actually generated using GPT-4o. A proponent could say, I mean, deeper network typically consume more memory and require longer computation batch. And then we can have an opponent that says, well, batch size is mainly constrained by available GPU memory, so that is correlated but not causal. So let me just skip to the more interesting one, because I mentioned before, power was affecting the shape. So the proponent can actually try to do something like, well, if you know in advance how much power you would be able to consume, then that might affect the resulting of your own design. But the opponent is actually putting forward, I believe, a very strong argument. Shape is the default training, and therefore is happening before measuring power. So there is a wrong temporal order in here. So just to conclude, using LLM as a source of knowledge for discussing about pros and cons of links is allowing us to generate structured arguments. This is what I showed you before, is just in natural language, but we can do clearly more structured arguments to assess or refine causal links. Now, sure, we can use LLM as pre-trained, we can use LLM as part of a retrieval augmented generation system, you can do something more sophisticated type of reasoning here. And yes, we are using LLMs, which are very energy hungry, to reduce the power consumption, for instance, of large language models, training of large language models. This is how innovation works. We need energy if we want to describe better what is happening behind some situation and improve that. So our position here is that our goal is not to use less energy, but to be smarter, to justify our use, and to be efficient in using. Now, this is joint current work, and we are planning to submit within whether for a conference call or directly for a journal, because the body of work is becoming substantial, but there is still a lot that we are trying to address, in particular in the prompt engineering, because prompt engineering, unfortunately, is very sensitive to the type of LLM we are using, and also some LLMs allowing us also the possibility to use some tooling for embedding augmentation semantic solvers inside other. So there are not experimental design problems here that we still need to crack down to the very bottom. But we believe that the potential is substantial, and of course is very much in line also with what Gianfranco was describing in terms of identifying counterfactual. We start from Judea work, but we can probably encompass also other type of reasoning in here, other type of argumentation schemes, and also what Luca described in terms of dialogue games is very similar to what we were already thinking in terms of embedding argumentation in this type of line of thinking and reasoning. So with this one, I thank all the co-author and collaborators for this type of work. I thank you for your time and your patience, and I welcome any questions you might have.
Thank you. Any question? Okay, there are no questions from the audience, so we are a bit late. Not a bit late, we are very late, so to proceed. So thank you, Federico.
Thank you very much. Enjoy the rest of your day.
Okay. So
Yes.
the session.
So the session is closed. We start immediately with the next one. So please welcome Professor Michele Flammini, which is the chair, and also I ask also the other speakers to come here so that we can be faster. Michele, the floor is yours.
Thank you. Good morning to all. The slides.
We will have the coffee break in the middle of the session, around 11:15. So, c'è un telefono, Sergio, è il tuo? Sì, dovrebbe funzionare.
So, good morning to all. I'm going to report about the activities of the work package 9.2, which deals with interactions among greenware agents, and I'm co-supervising this VP with Valeria Fionda. Our VP concerns systems in which there are autonomous agents that interact, taking actions that have an impact on the environment. And we are structured in 5 tasks. So the first task concerns the definition of models that try to capture the outcomes of these systems and their performance. Task 2 is concerned when these performances are too suboptimal with the design of coordination mechanisms or incentives that lead to better solutions. Task 3 concerns mechanisms to elicit the preferences of the agents when they are not known, and and algorithms for and learning algorithms for learning these preferences from samples. Task 4 deals with graph mining of the complex networks that arise during the interaction of these agents. And finally, task 5 concerns the temporal reasoning of the agents in terms of temporal frameworks that try that help us to reason about the temporal evolution of these multi-agent systems. As Francesco says, this is one of the most crowded APs because there are even 4 external units participating through cascades. In particular, while task 2 is led by myself, task 3, sorry, is led by myself, it is internal to Unical, and task 5 is led by Valeria Fionda, and is internal to Unical. The other tasks are benefit of the participation, respectively. Task 1 of the University of Chieti Pescara, supervised by Luca Moscardelli. Task 2 has the participation of the University of Salento, led by Vittorio Bilò. Task 4, even 2 cascades, one from the Gran Sasso Science Institute, led by Gian Lorenzo D'Angelo, and the other one from the University of Messina, led by Pasquale De Meo. Thanks to this overall participation of people, we had quite a fervent research activity during the last year, both inside the single units, cascades or Unical, or in collaboration between the units, between cascades, between our VP and other VPs, and between our spoke and other spokes. This led from the last year, more or less, to a good number of papers. We had roughly 35 papers, of which a good percentage was published in top-ranked venues, 12 in A-star conferences, 4 in Q1 journals. I'm not going to report about these activities because we are late, so here is a list of the publications, and I leave space directly to the people involved in the unit and in the cascades that will tell you a bit more about the single research activity that are pursued in their units. Thank you. And so I call first speaker, Giovanna Vardicchio, which will tell us about fair division with social impact. Thank you, Giovanna.
Anyway, all presentations will be made available in our team, so after you can see, you can find all.
Okay, thank you, Michele, for the introduction. And today I will talk you about a joint work with Michele Flammini and Gianluigi Greco, which is fair division with social impact. Now, our contribution in this work is to introduce the social impact aspect in the fair division model. Since I do assume that most of you are not familiar with the fair division framework, I will start with describing such a framework. And in a nutshell, what we have is that fair division task is to distribute a set of resources among agents in a fair manner. And the nice thing of this model is that when we want to think about possible example, we can start with very simple example in real, in everyday scenarios. As for example, we are in academia, and most of the time it happens that we have time slots for the lectures, and we want to distribute these time slots among professors that we may possibly fight for their most preferred time slot. And so maybe we want to be fair among these professors, assigning these time slots fairly, whatever fairness means. Or other example includes dividing asset or inheritance, or even dividing land. Now, among these examples, we can already see that the type of resources that we can have may possibly be either divisible or indivisible resources. And while the first part of the literature has been focusing on divisible resources, in this talk I will be describing you the setting where the resources we have to distribute to people are indivisible instead. So let me give you roughly the model in a very simple way. We have n agents, and we have m, in this case, indivisible resources. And this, the objective of our objective is to assign these resources to the agent, which means we have to partition the resources and decide which agent will receive which specific set of resources that is usually called bundle. Now, our agent our agent have the evaluation among the resources, and in particular we can make the simplistic assumption that the agents are additive, for example, which means that each agent attributes to each one of the resources a value, and when they have to evaluate a subset of the resources, they simply have to sum up the values they give to the resources in their bundle. So while the model looks pretty simple, the hard part in this setting is to determine, first of all, what is fair, because we may have different concepts for defining fairness. As for example, we can start with a type of solution concept that is called comparison-based, which means we look at the outcome, so the partition among the agents, and when we have to evaluate what we received, we compare to what the other received. So MV freeness assumes that if I look at what I received and I look at what you received, I still think that what I received is better than what you received. So I'm not envious of you. Another type of solution concept is instead shared-based notion, which is pretty simpler, because instead of looking at what the others receive, we have in mind a threshold value that we want to exceed. And if we exceed that value in the allocation, we will be fair. So this is a way to think about fair solution concept. On one hand, we have solution concepts that are comparison-based. On the other hand, we have solution concepts that are share-based. Now, the problem of indivisibility arises when we want to have exact fairness solution concept. So, for example, here we have two agents and one item, and there is no way to assign this item fairly according to the solution concept I already defined to you. And without going too much into the details today in fair division solution concept, let me tell you that fair division has considered these kind of scenarios and has found solutions to deal with this indivisibility constraint. And there are many solution concepts. I would not really mention them, but they will be the solution concept I will consider, so this is why I at least roughly mentioned to you that there are many ways to resolve the indivisibility constraint. But what I want to focus on today is what we actually introduced in this model. And in particular, we started noticing that in the fair division framework that I described to you so far, what we have is that the focus is on the agent, and the item have to be distributed, on the evaluation of the agent, and how to fairly distribute to the agent. But our question was, what happens if this allocation problem has an impact on society? So in this simple example where we have some items that probably only the agents that are involved in the system do care about them, there may be other scenarios where we can apply fair division model, but has a broader impact on society. So let me start describing our model with an example, or at least a toy example, but just to give an idea of the flavor of which kind of problem we hope that our model can deal with. So imagine the government has to assign some green strategies to the industries, to some industries. And now this, what can happen is that the allocation problem involves the industries as agents and the green strategies as the resources. But now the industries can have the reason why I want to be fair about the allocation is because we can imagine in this system that the industries, if they feel that the allocation is unfair of these green strategies, they can drop out of the system, just to mention. So now the problem is that allocating a green strategies to an industry may have two different effects. One effect is for the industry itself that by implementing a green strategy, we can imagine they increase their profit because nowadays industries that are more sensitive to green aspect are more appealing to customers, for example. But on the other hand, giving a green strategy that is a strategy that will possibly reduce the emission has an impact on society. So in this case, the social impact we are considering is the reduction of the emission, for example. So more formally, what we did was to extend the fair division framework, adding a social impact function for each agent, which determines which is the impact of the agent when receives a certain amount of resources. And what we want to study in particular is the total social impact of an allocation, but at the same time, we want to be fair to the agent. So we add on top of the fair division framework, where the goal is to be fair to the agent, the further constraint that we want to be as much as possible good for society. And the natural way to measure this kind of two different objectives when we at first want to be fair is to at first consider what would be the best social impact of any allocation without considering the fairness constraint. And second, we consider what is the best social impact of the best fair solution. And considering the ratio of these two quantities, we can bound how much we are losing with the further constraints that our allocation has to be fair. The first question we had then was, how bad can be the impact of asking to an allocation to be fair when we have a social impact? And I have a simple example to give you the intuition how bad it can be. Imagine there are n available solar panels, 9 available solar panels, and we have 3 industries. These industries are identical in the sense that all of them have the same opinion of the solar panel, which are equal, but they are in different locations. Of course, different locations in different regions which have different weather will have an impact on society, on how good is the performance of the solar panel. So from that, a social point of view, the best would be putting the solar panel in a sunny region, I would say. But on the other hand, since these industries are equal, in all the solution concepts that we considered in our work, the most fair thing you can do is to evenly spread the 9 solar panels among the different industries. And this already shows that if we compare to the optimal solution, the solution that we have 1/3 of the social impact that we would have in the optimum. And we can generalize this simple example to work for an arbitrary number of agents, which would mean that we will have a price of fairness that is at least n, where n is the number of agents. So to give you an overview of our results, as I told you, I didn't went into the details of the specific fair solution concept because I have no time, but assuming that these are well-established solution concepts, what I already showed with my simple example is that the lower bound of the price of fairness is at least the number of agents, roughly. Which means that the results that we can find are pretty bad anyway, because the lower bound is linear in the agent. The more are the agent, the worse would be the result of requiring fairness. And the good news is that we proved that most of the solution concept that we consider, these bounds are tight, so we can be tight to the lower bound, and this is achieved by a polynomial time algorithm. Having an upper bound here means that I can find a solution that is fair and has exactly this linear price of fairness in the number of agents. But the problem remains. We have very bad performances, and the next question we had was to figure out what is the cause of these bad performances in our model. And what we realized is that essentially fairness and optimality in the social sense are 2 orthogonal objectives, and the reason why is because these 2 functions, so far I made no assumption on any correlation between them, which means that the optimum is the social optimum is far to be fair. But what I want to also stress is that it's also the selfishness of the agent that is making these objectives orthogonal, because the agents actually do not take into account their social imprint in the fair allocation problem. When evaluating fairness, they only care about their profit, in the example of the industries, but they don't care about the reduction of the emissions at all. So our question was, what would happen if the agents instead are aware of their imprint? So we introduced a notion that is designing fairness in a way that is also socially aware. And to roughly describe what is happening when the agent has to evaluate if the outcome satisfies them, they also take into account the impact they have and the impact the others have. So if I have to determine, for example, envy, if I would envy you because you have more than me, but you have a better social impact, I have to admit that essentially you are better than me in performing that, and I cannot really envy you. I will only envy who has a worse imprint than me on that set of resources, which is introducing the social objective into the evaluation of the agents. Now, as I told you, because of indivisibility, we have that this kind of exact notion do not exist, but we introduced a relaxed version of it. And for this relaxed version, we were able to show that an optimal and fair solution exists, which means that we can have a price of fairness that is equal to 1. So this is an overview of what we did. So we introduced the social impact in the fair division framework, and we figure out how to solve the very bad performances of fairness in this setting. So let me conclude saying that this is a very first step what we did. So we introduced this dimension into our fair division framework that was like our first case of study. Like we were already working in fair division, and we decided to introduce this green dimension, this social dimension in it. But there are many things that we still have to do because we had this very distinct result. First of all, we assume that the agents were aware of their impact, but we cannot assume that they are so unselfish, like so altruistic for society. So the next step would be either to look for a trade-off, something like the agents are not completely selfish, the agents are not completely aware, maybe we want to look something in the middle and see how the performances of the fair solution may change in this scenario. A second thing is that even if there are not such kind of agent, we can design incentives to make the agents aware. Because in our work we saw that aware agents will have a better imprint, but they may not be aware, and for this reason we need to introduce some kind of incentive in making them aware. And finally, the third thing is that in this talk I focused on fair solution that eventually maximize somehow the impact, but maybe we can reverse our perspective and think about among the socially optimal outcome, which are fair or which are good for our agent or selfish agent. So this ends my overview on our contribution, and happy to receive questions.
Thanks, Giovanna. So any question from the audience? Go Pasquale? Yes?
Okay, thank you a lot. Very nice presentation. Like it a lot. The one question, can you modify your objective function to include the correlation effect? I mean, you have, I receive all solar panel because I am in a sunny region, but I have to sell electricity to all other industries at half of the price. A kind of compensation mechanism. I receive all resources, but I am in obligation to donate my services at lower price.
Okay. Since we were considering a more general framework, in a more general framework, there is no side effect, not really side effect, because the side effect is the social impact, it's more like externalities, I would say. But we could possibly introduce an externality motivating in that way. That could be a way also to compensate and can be a kind of incentive. It's actually a good point of view, I think, because this would reply to the second point, because the incentive comes from the systems and not from the government, like in my example. So there is nothing about that, but we could consider something like that.
Thanks a lot.
Very nice.
Thank you. Any further questions? Okay, thanks again.
Thank you.
So the next speaker is Daniele Carnevale from the Gran Sasso Science Institute of L'Aquila, approximating optimal labelings for temporal connectivity. The ground is yours.
Thank you.
You might need this.
Hello, everyone. I will present this joint work I've done with Gian Lorenzo D'Angelo and Marty Dolson. Let me start from an example scenario. Imagine that you have a bunch of cities that want to exchange packages through a parcel warehouse. So in the picture, we have L'Aquila, Roma, and Cosenza that want to exchange packages. And we will make some assumption about this problem. We will first assume that each city has its own vehicle. So every city has its own vehicle to deliver its packages, and a trip takes 1 hour, and it's intended as a round trip. So a trip that starts at 7 a.m. from L'Aquila will reach at some point in time the parcel warehouse and will be back in L'Aquila by 8 a.m. And overlapping trips cannot exchange packages. So if there is a trip at 7:45 a.m. from Cosenza, it cannot take the packages incoming from L'Aquila. Fourth assumption is that each city has at least one package to send to every other city. And our problem is to schedule the trip in such a way that every city receives all its incoming packages. Let me go through our first scheduling example. So we have at 6 a.m. a trip from Cosenza, which will bring in the parcel warehouse the outgoing packages. The same for the two concurrent trips at 7 a.m. from L'Aquila and Roma. Then at 8 a.m. Cosenza goes in the parcel warehouse and takes the incoming packages from L'Aquila and Roma. And at 9 a.m. Also L'Aquila and Roma will take their incoming packages, and so the scheduling is done. And we have 6 trips and 4 time slot in this case. But maybe the problem is a bit too simple in this way. So we have 2 natural constraints. The first one is a bounded number of time slot. This might result in reducing the infrastructure cost of the scheduling. And the question is, we have done it with 4 time slot. Can we do it, for example, with 2 time slot? And the answer is yes. We have scheduling with just 2 time slot and 6 trips, in which each city at 6 a.m. brings its outgoing packages in the parcel warehouse, and at 7 a.m. it takes the incoming packages from the parcel warehouse. Another natural constraint is to minimize the number of trips. This might reduce, for example, the greenhouse gases produced by the vehicle. And the question is, can we do it with fewer than 6 trips? And again, yes, we have a scheduling with 5 trips, which exploits the fact that Cosenza goes in the parcel warehouse when all the incoming packages are already there, and it obviously brings in the same trip all the outgoing packages. Here we have a summary of what I said till now. We have our 3 schedules and the assumption and the restriction, and we add one more assumption to this, that is, what if we have a general network in which each location might serve both as a warehouse and as a city? we add this to our assumption, and now the problem becomes, what is the minimum number of trips needed to deliver all packages within a given time? And we model this problem using temporal graphs. What are temporal graphs? They are just graphs where each edge is assigned a set of labels that indicates its presence in time. So for example, the edge AB is labeled with the set 2, 6, indicating that it's present at time step 2 and 6. A central notion in temporal graphs is the one of temporal paths. A temporal path is a sequence of edge label pairs such that the edges form not a classic path, and the sequence of label is strictly increasing. At least this is the definition of temporal paths that we used in this work. And for example, CB4BA6, it's a temporal path, while CD3DA3, it's not a temporal path as the labels are not strictly increasing. And if every vertex can reach every other vertex through a temporal path, we say that the temporal graph is temporally connected. So in the picture, A can reach every other vertex, and so B, C, and D, and thus this is a temporally connected graph. On the right, we have an example of a graph that is not temporally connected because C cannot reach A. We are ready to introduce the problem that we studied, which is called minimum aged labeling problem. Says given a graph G and an integer A called the age, assigned to each edge a possible empty set of label in such a way the following conditional. So the graph is our network, and we want the temporal graph to be temporally connected. This is every vertex can reach every other, and so every city can send these packages to every other city. All labels are less than or equal to A. This is the bound on the number of time steps. And we want that the total number of labels is minimized. This problem was already studied by Klaubas et al., and they established that the decision version of MAL is MP complete when the age is equal to the diameter of the input graph, and they are both equal to 10. We show that the decision version of MAL is MP complete when the age and the diameter are both greater than or equal to 2. On the hardness of approximation side, I highlight this result will be for the case when the age in input is equal to the diameter of the graph in input. And we have a previous result from Mercios et al. That proved that the directed version of MAL is APXARD. This roughly means that we cannot hope to approximate the problem arbitrarily close to the optimum. And we proved that MAL is not approximable better than log n under the assumption that P is different from MP. And actually for the case in which A and the diameter of the graph are both equal to 2, we have an approximation algorithm of the same ratio of the hardness, and proving that the hardness is tight in this case. while for the case greater or equal to 3, we proved that under the assumption that MP is not included in deterministic time of 2 to the poly log of n, we proved that this is not the problem, it's not approximable, better this strange factor 2 to the log to the 1 minus epsilon of n. On the approximation algorithm side, this result will be for the case when the age is greater than or equal to the diameter. And we have 4 main techniques. The first one is what I call folklore labeling, which is an algorithm well known in the temporal graph community, and this allow us to approximate the problem quite close to the optimum when the age in input is at least 2 times of the radius of the input graph. Other 2 techniques that are pairwise spanner and additive k-spanner, which are a classic problem in static graph. We adapted them to work in the temporal case, but at the cost of paying a factor equal to the diameter of the graph in the approximation. While the fourth and last technique, it's based on a definition, on a tool developed by Gold and Chaudhary called dominating and set pair. They used it to estimate the diameter of the graph in fast time, while we adapted it to work on temporal graph, and this results in 2 approximation algorithms which do not depend linearly on the diameter of the input graph. As an open question, we wonder if MAL is NP complete when the age is different from the diameter, and the same question for inapproximability results. And while on the approximation side, we wonder if the strain factor of hardness can be matched when the age and the diameter are greater than or equal to 3. Thank you.
Thanks, Daniele. Thanks. Any question? No question. So I have a question. Did you consider restricting the topology of the network? So did you consider the restrictions of the topology of the network? Can you improve some factor?
It was considered by some previous paper that, for example, when the input graph is DAG, a directed acyclic graph, then the problem becomes polynomial. But and otherwise, there are some results on the restricted graph, but about FPT algorithm.
Okay, thank you. So if there is not any question, thanks to the speaker again. So since we are out of schedule, we anticipate now the coffee break. And what time should we be back?
I think in 20 minutes.
20 minutes, okay? Thank you.
Sì, no, visto che erano pronti, se non sbaglio
prima di Napoli, io dovevo venire a Napoli, non potuto venire perché stavo praticamente incidentato, sono caduto il 14 agosto, è andava tutto bene, dopo un paio di settimane. Prima c'era la citazione tra dati in compressione e Roma, si è rilasciato il testo. Io non lo sapevo. E adesso ancora una salita, è rimasta lì che a Napoli
sarò nella sessione di dopo.
Ah, nella sessione di dopo? Allora se la carichi su Dropbox te la scarico poi direttamente.
Portato il computer.
Vabbè, mettilo, dai, fallo direttamente.
Qui?
No. Poi, aspetta, download. Qua, tu sei VP6,
sì.
No? Vai. E la copi qua.
Questa la tolgo?
Sì. Questa è la nuova, giusto?
Sì,
ok.
Perfetto. Grazie.
Comunque magari, aspetta, fai espelli che sennò... Vabbè, ormai è andato. Magari mettila comunque quella corretta poi su Dropbox.
Okay, we start again. So the next speaker is Luca Moscardelli from the University of Chieti Pescara. The title of the talk is Blackout Games.
Thank you, Michele. This is a joint actually this is a working on paper, and this is a joint work with Giampiero Monaco and Raffaele Mosca, and we come from the University of Chieti Pescara. So the motivation for our study is given by the fact that the increasing demand for energy naturally leads to an increasing risk of blackouts. And a blackout can imply a waste of resources and also an increase of pollution. Why? Because additional energy sources must be exploited in order to deal with the possibility of a blackout. So for these reasons, we study blackouts occurring in the strategic interaction among agents. And our first contribution is the design of a model for this interaction. Roughly speaking, we consider a setting in which agents requires an amount of energy. The provider of this energy could go into a blackout whenever the requirements of the agents exceeds a given threshold, and each agent has to pay a cost for the energy she obtains from the provider. More precisely, we have n agents requiring energy from a provider in a given time period. And we assume that this time period is divided into t time slots. We can think that the time period is a day and that the time slots are the hours of the day. And every agent has a demand of di units of energy within the whole time period. And every time slot has a capacity, MT. The capacity is the threshold, and if the requirements of energy in that time slot exceeds this threshold, then the provider goes into blackout in that time slot. We also assume that the sum over all agents of the demands is at most the sum over all time slot, or the sum of the capacity of all time slots. It means that it always exists in our setting a solution satisfying all the demands without going in blackout. The strategy for an agent is a t-dimensional vector of non-negative integers in which every component indicates the number of energy units required in the considered time slot. And we have to satisfy the constraint that the sum of energy units required along all time slots has to be at least the demand of the agent. As usual, a strategy profile is given by a vector with a strategy for every agent. So we have now to define which is the energy obtained by an agent at a given time slot. We have to distinguish between two cases. If the time slot doesn't go into blackout, then the energy obtained is simply given by the energy required, by the strategy STI of agent I for time slot T. In the other case, that is, there is a blackout on time slot T. In this case, the energy obtained by agent I for time slot T is 0. So we assume that when there is a blackout, all the agents require energy for that time slot do not get any unit of energy. The cost incurred by agent I is simply given by the sum over all time slots of the product between the amount of energy obtained, which is RIT, times PIT, where PIT is the cost that agent I has to pay for 1 unit of energy from time slot T. Moreover, there is this penalty function pi I, which arises in the case in which there is a time slot, there is a blackout on a time slot. Roughly speaking, every agent has to pay a very high cost P for each unit of energy that she doesn't obtain from the provider. Okay, so we say that a game is simple if the unit cost experienced by agents for a given time slot T is not agent dependent. So PTI is equal to PTJ for any I and J, for any couple of agent I and J. And we also consider what we described in the previous slide was the total cost of agent I. We also consider a variant of this cost, that is the per unit cost of agent I, which is obtained by dividing the total cost by the demand of agent I. And it's worth noticing that the per unit cost makes sense only for simple games, because in non-simple games, this denominator di could be included in the per unit cost PTI, which is player specific. Okay, this is an example of a simple game. We have 3 agents and 4 time slots. In the top left table, we have the demands of energy of every agent. And in the top right table, there are the capacities of the time slots and the prices, the unit price for 1 unit of energy experienced by the agents for that time slot. Since we are in a simple game, these costs, which are the last column of the table, are not player dependent. So if we consider this strategy profile, we can notice that the obtained energy is almost equal to the requested energy in particular, it is exactly equal for the first time slot, the blue time slot, the green time slot, and the red time slot. But we have a blackout occurring in the third time slot, in the yellow time slot, because the capacity of the third time slot is 2, but we are requiring in total 3 units of energy. And this blackout make the costs of agents 2 and 3 have this high P cost, this penalty cost, because both agents 2 and 3 do not obtain all the unit of energy corresponding to their demands. Notice that even if the blackout also concerns the first agent, that agent is obtaining 5 units of energy, and for this reason, the first player is not incurring in the penalty cost P. Okay, so we consider the two standard utilitarian and egalitarian social welfare function, which are defined as the sum overall costs and the maximum cost overall agents. And we study this problem, both in its centralized version and in its game theoretical one, by using a Nash equilibria as stability notion. In particular, we also evaluate the efficiency of Nash equilibria by the well-known measures of price of anarchy and price of stability. I will introduce these notions when I will show the relative results. So, for what concerns the optimization problem, and when considering the utilitarian social welfare, the problem is easy. It's polynomial time solvable by a reduction to an Hitchcock-like transportation problem. But things are more difficult for the egalitarian social welfare function. In fact, in this case, computing the optimal solution is NPR'd even in the simple setting when the costs are not player-specific and with two agents, both for total cost and for per unit cost. And we have a reduction from the subset sum problem, and becomes strong and NPR'd for general instances with a reduction from 3 partition. On the positive side, we have a fully polynomial time approximation scheme for a constant number of players, so matching the inapproximability, the complexity result. And we have an approximation algorithm with approximation ratio being the minimum between t, which is the number of time slots, and the Euler number times the natural logarithm of dmax, where dmax is the maximum demand among all agents. If we have time, I will sketch the proof of this last result at the end of the presentation. Okay, Nash equilibria always exist for these games. In particular, for simple games, it's easy to completely characterize them because in this case, all cheapest time slot has to be used at equilibrium. For non-simple games, this characterization cannot be provided, but anyway, a Nash equilibrium can be computed in polynomial time by performing Nash dynamics starting from the empty state and converging in at most n steps. About the convergence to Nash equilibrium, for simple games, convergence is obtained after a linear number of best response. We are speaking about convergence starting from any state of the game. While for non-simple games, the convergence is guaranteed in this number of steps, number of time slots times the sum over all agents of their demands. And this is a tight bound. We have a matching lower bound using exactly this number of best responses. The price of stability of the game is 1. This is an easy result because it's easy to see that under the utilitarian social welfare function, any optimal state is a Nash equilibrium. And also under the egalitarian social welfare function, even if it doesn't hold that any optimal state is a Nash equilibrium, but there exists always an optimal state being a Nash equilibrium. And for this reason, the price of stability is 1. What is the price of stability? The price of stability is a measure of efficiency of a Nash equilibria, defined as the ratio of the social welfare of the best Nash equilibrium over the social optimum. So since the optimum is always a Nash equilibrium, this ratio is trivially 1. And for what concerns the price of anarchy, which is instead another measure of efficiency defined as the ratio between the worst case Nash equilibrium and the social optimum, we have that for non-simple games, this price of anarchy can be unbounded. This is a very simple counterexample showing these results. We have 2 agents and 2 time slots. The demands of both agents are 1, and also the capacity of the 2 time slots are 1. And as you can see from the first graph showing the instance, the cost of the first time slot of 1 unit of energy of the first time slot for agent 1 is 1, while the cost of the same unit of energy for the second agent is B, which with B being much bigger than 1. So in the optimal solution, both agents pay 1, and but there exists a Nash equilibrium in which one agent pay 1 and the other one pay B, thus showing that the price of anarchy can be unbounded. For simple games, we obtain better bounds because we are able to prove the following these tight bounds as shown in the table. So for total costs, under utilitarian social welfare, the price of anarchy is 1, and under egalitarian social welfare, the price of anarchy is n. In the case of per unit cost, the price of anarchy is equal to the maximum demand of overall agents, both for the utilitarian and for the egalitarian social welfare functions. So, I don't know if I have time for this sketch. Maybe yes. Okay. Very fast. I try. I just to give the flavor of the proof. We are in the setting of the egalitarian social welfare function, and we want to compute a solution approximating the optimal solution by this approximation factor. So the idea of the proof is to do a binary search on a target value B in order to find the minimum value of B such that the max flow of a maximum flow problem that I'm going to show you is at least actually exactly equal to the sum of all the demands of the players. So this is the instance. You see there is a source node and this S, a destination node T. Every agent corresponds to a circle blue node. Every time slot corresponds to a square blue node. And there are also these yellow nodes. There are log B yellow nodes for every agent. And these yellow nodes partition the time slot with respect to the cost of this time slot for the player corresponding to these yellow nodes. In particular, group ij is connected to every time slot T such that PTI is between B over 2 to the j and B over 2 to the j minus 1. So we can prove these two properties. The first property is that if the maximum flow of the instance defined on parameter B is less than the sum of all demands, then the optimum solution is at least is greater than B. And on the other hand, the second property states that if the maximum flow of the instance defined on B is exactly equal to the sum of all demands, then this maximum flow induces a solution with social welfare being B times the minimum between T and 2 log D max. So the first property is very easy to check because the maximum flow on the instance defined on B and induced by S star is equal exactly to the sum of the demands of all players. And for the second property, we can play with the, I not said that the weights on the edges are the capacities of the flow network. And by playing with this capacity, we can show that the social welfare computed on the profile on the state S is at most B times T because of this green cut on the flow network, and is at most 2B times log D max because of this red cut. So this is just to give a flavor of the proof. There are several open problems from this work. First of all, understanding the best approximation that can be efficiently computed for the egalitarian social welfare, because we have a gap from the strong NP hardness and the approximation, the logarithmic approximation with respect to D max and the linear approximation with respect to the number of time slots. Moreover, in non-simple games with egalitarian social welfare, computing efficient and unstable outcomes in polynomial time is an intriguing open question. Also considering other notions of stability, such as strong Nash stability, core stability. Performing an evaluation an experimental evaluation of the results, because for now we also have theoretical results. Considering different cost functions for players, for instance, capturing the fact that unused energy cannot be stored, and also finally studying a repeated version of these games. For instance, we can assume that for each day we repeat the game by exploiting techniques from repeated games in game theory. Okay, thank you.
So, any question? Why? Vittorio?
Yes, I have a sort of an observation that can be also considered a question. In the price of anarchy result, so when you put that for non-simple game it is unbounded, I think, can you refine the result to prove that it's bounded within the maximum discrepancy between prices?
Yeah,
because
of
essentially
course.
is what you obtain in the lower bound.
If we assume that there is the ratio, let's say, between the maximum, the minimum value of cost of a given time slot for among overall agents is bounded, then this bound applies to the price of marketing as well. Yeah, thank you.
Okay. Any other question? No, thank you. I will make a question later on. So the next speaker is Pasquale De Meo from the University of Messina, synthetic data generation for graph dissimilarity computation. Thanks, Pasquale.
Thanks a lot. Okay, thanks also to the organizer for your huge efforts, and Sebastiano, who is here in the room and is helping me. Okay, I am the PI of a project about the computation of graph similarity. And what are the motivation of our work? Okay, many problems from real life can be encoded as graph, and in several cases it is crucial to accurately compute how two graphs are similar. For instance, we could have two chemical compounds which differ just for a few bounds, and we would like to check if a drug, which we know could be used through comparison for other purposes. Another example which is interesting in my opinion is about anti-money laundering. Laundering is the process by which criminals use intermediaries, shell companies, to wash money coming from illicit activities and transform them into fully licit activities. So, for instance, money from drug trafficking to restaurant, just to an example. So, financial institution, for instance, Banca d'Italia here, provides schemes which are highly suspicious, and for instance, an highly suspicious schemes could be a ring of four intermediaries which are used to wash this money and to inject it in the financial system. And so in this case, our goal is to detect if, given a large transaction network, to detect if there are some patterns which are close to other patterns which experts have considered as suspicious. Networks are also useful in the analysis of brain. Okay, brain is often modeled as a connection of neurons, and so detecting anomalies between neural activities is used sometimes for diagnosis purposes. And last example, I could have a social network of my students. I teach computer science for humanities. I guess I am one of the few persons here in a non-technical department. And so my question could be, do my students have similar communication patterns, similar behaviors than students in other departments enrolled in other kind of studies? And of course, the list of potential application is not limited. Graph similarity has been used to query graph databases to detect if in a network, in a road network, there is an anomalous flow of vehicles, to use interaction between proteins to predict disease, and the list of examples is very huge. Okay, there are a lot of similarity measures. One of the most popular is the graph edit distance, which can be regarded as the natural extension of the string edit distance problem that you teach, not me, at your program algorithm courses. Essentially, you have to graph. You are allowed to consider operation like add a node, delete a node, add an edge, delete an edge, change the label associated with node and edge, and each of these operations, which are called edit operation, comes with a cost. So, for instance, in the slide you have a graph 1, you add a node, which is node 6 red, then you connect node 6 with node 4, you obtain the graph 3, so this means that the graph edit distance between these two graphs is 2. Okay, so it was introduced about 40 years ago, essentially in the field of computer vision, but today is used in a lot of practical contexts. But unfortunately, the exact computation of the graph edit distance between two graphs is much more complex than the computation of the edit distance between two strings. Okay, the problem is NP-hard, and it is also hard to get a good approximation of the problem. And so, in the latest years, a lot of approaches have been tested. Some are classical ones, for instance, the application of search algorithms like A*. Relatively recently, 6 years ago, more or less, someone suggested to formulate the task of approximating the distance of two graphs as a learning problem. Okay, this is the first approach to solving this problem. Is called, the architecture is called SIMGNN, Similarity Through Graph Neural Networks, and it has been extended in a number of ways. Okay, this approach seems very interesting because they produce very accurate results. They beat approaches based on heuristics, and also at inference time they work very well. But we are not sure that the evaluation about this approach is fair. And the main reason is that we lack of good datasets to carry out our evaluation. We found just 3 datasets, 3 public available datasets for running our comparison, But in most cases, for two samples of this data set, we don't have the true distance. What people do is to apply 1, 2, 3 more heuristics to get 1, 2, 3 more approximation of the true distance and to get the best one as a surrogate of the true value. And of course, this makes this does not offer any guarantee that our evaluation is correct. So the first goal that we consider in our approach is, can we construct good data sets that perhaps can be used to train existing model and to check if a model is actually as good as it promises? And we try to give an answer, and essentially, we formulate the problem of generating synthetic dataset as a sampling problem. In other words, we consider a very, 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 very large of graphs, which are potentially candidates to be included in our datasets, and we transformed our problem in the problem of sampling graphs from this large space. To make our computation feasible, we made two assumptions. Firstly, we assume that node ordering is fixed, okay? And actually, this is not big constraints in the sense that we can easily relax it, but essentially, if we make this assumption, so if nodes are associated with an order, the task of computing the graph edit distance is much easier because it is equivalent to compute the number of entries of the two matrices of two graphs and to count how many entries are different. Essentially, this means that if we have two graphs and the node ordering is fixed, then we use the adjacency matrices of these two graphs and we count how many entries of the first matrix differ from the entries of the latter one. And clearly, we move from an hard problem to a much, much, much easier problem because the number of entries is quadratic in the number of nodes. Okay, so with these premises, we start with this configuration. As I said, we have a very, very large space of graphs. These are a subsample of graphs with 5 nodes, and you observe that samples in the same space could be very different in the sense that we could have dense structure, for instance, graph 4, and we can have very sparse structure, for instance, graph 10. Okay, so how can we sample in this space? Okay, we considered two strategies. The first one is a standard Markov chain Metropolis hastings algorithm, in the sense that at the 0 iteration, we start with a seed graph. At the next iteration, we are allowed to do 3 operations: remove an edge, and in this case, we removed an edge, or do nothing, which is what we did in the second iteration. So from 1 to 2, we have no changes. The graph is unchanged. At the third step, we had an edge, and we continue. And in this case, if we model our space as a Markov chain in which nodes are each of this graph and edge model transition, we can move from any point of this space to any other point of this space. To any other point of this space. Okay, to any other points of this space. Okay, for this sampling strategy, we have. Okay, thanks. Okay, for this sampling strategy, we have results because our algorithm is an example, is a Metropolis hastings algorithm. We are sure that the sampling procedure is unbiased in the sense that there is no point in the sampling space which can be ignored by our procedure. Of course, we could require a lot of time to explore all regions of this space, but if we have time to run our procedure if we can run our procedure for a reasonable amount of time, we will not leave out any possible sample. To be more precise, this is a kind of sampling algorithm which is known as slice sampling, which is quite popular in the literature about Bayesian network. Okay. So this is the first strategy. The second strategy is radically different. Such a strategy is called all. It depends on a parameter called flipping probability. At each time step, we flip all bits of our matrix with a probability P. So this means that in one step, we could move from state 0, okay, this graph, or an even more sparse graph, to a graph after just one iteration, which is totally dense, which is a complete graph. Okay, for this old strategy, we have also two results, and in particular, the first one is this is an unbiased technique, in the sense, in this case, we can pick any potential graph which exists in our space. We do not exclude any potential instance, but we were able also to compute in exact fashion the probability of jumping from one of these samples to another samples in a fixed number of steps, which avoids us to compute heavy matrix bivector operation. Okay, so we have these results, and okay, we implemented our algorithm. The code is available on Git. This is part of the product of the project, and we hope also to release datasets to offer to the community interested in this topic. As I said before, there are exactly 3 datasets available for our purposes. The first one is AIDS. This is a database of chemical compounds, which is released by National Institute of Health in US. IMDb, which is a database of interaction between actors in movies. IMDb stands for Internet Movie Database, and essentially they are Ego networks. And the last one is a collection of program dependency graphs between function of the Linux kernel. Okay, in some cases, IDEs, we have features because they are chemical compounds, so we have information about the molecular weights or other physical and chemical properties. In other cases, we don't have any label associated with our database. Okay, what we did, for each of these, we extracted a number of seed nodes, give these seed nodes to our algorithms, and ask them to generate dataset. Of course, we have the luxury of generating as many samples as we want, because the procedure essentially requires to generate sample random numbers, so it is very, very, very fast, even on commodity hardware. Okay, we did a comparison with 2 strategies which have been largely studied in the field of graph neural network theory, in the sense that the people working in a graph neural network face the problem of dealing with a few datasets. So in the latest years, there was a huge effort to create artificial datasets, and for instance, Google has a nice tool called GraphWorld. 2 minutes, I have finished. GraphWorld, which is publicly available to train graph neural network. The 2 strategies are called Merit, published at EJKI, and essentially we fix a parameter P is a budget, a number of edge. We first delete at random P edge from our graph, and then subsequently we add P edge. Of course, we have 2 variants, in the sense that we can allow deleted edges to be immediately added again to the graph, or vice versa, we can forbid edges to be reintroduced. And another strategy is known as uniform rewiring. We have 2 parameters that control the process, P plus, which is the probability of adding a new edge, P minus, the probability of deleting an edge, and we consider 2 configurations. Okay, P plus is bigger than P minus, in the sense that you go toward denser graph, you tend to densify your graph, or the opposite strategy, in which you tend, your goal, your objective is to sparsify your graph. Okay, how does our approach compare with the existing one? Okay, for methods by uniformly adding and deleting edge, we found that they generate graphs as you see in this slide. In other words, these graphs, analyzed in terms of structural properties, that is their page rank, their degree distribution, their closeness, their clustering. Clustering is how many times a node appears in a triangle. Okay, these graphs are very, very, very similar each other, which is bad for us because we would expose our algorithm to data which are very similar each other, and so we think the algorithm would see many examples which are closely related each other, and we think that the training process is less robust. We would like that our algorithm sees examples which are very different from a structural standpoint. For other approaches merit, instead we have the problem that you depicted in the slide. The cube, the big cube, is potentially the space, the whole space of synthetic graphs that they could generate. But these strategies are bounded to small regions of this hypercube. And this means that the datasets that they generate are biased because they totally neglect examples which could be useful for our experience. So we think that we made a little advancement to the state of the art in the sense that we can produce for the community big datasets in a reasonable amount of time, and our datasets are both unbiased and structurally different. And the results of our study is now under review. Okay, the lesson that we learned suggested us to formulate an art problem computing the JED through a tool that in the latest years has been largely used in the machine learning community, which is optimal transport theory. This is not a new theory because the inventor was Gaspar Monge, who was an engineer during the Napoleon Bonaparte era. Okay, and this tool have been applied in machine learning in the latest years. So our goal is to formulate our problem as a problem of optimal transport. What is the energy that I need to modify a source graph to transform to another one? And we would like to add some regularization constraints. In the sense, among all possible transformation, try to penalize a transformation if, for instance, it maps a node with a high degree to a node with small degree, or if it tries to map a node which as a surrounding neighborhood well connected to a node which is isolated. We are working on the theoretical formulation. If our intuition are correct, we could use efficient methods, Frank-Wolf or conditional gradient method to solve it. And this should be, in our opinion, a step ahead toward energy efficiency, because not only our algorithms are fast, but also because they could be implemented in CPU, and usually the energy consumption of a GPU is much smaller than a GPU. So I hope to not get you bored, and I hope to not have consumed too time, and please allow me to thank you for your attention after this long morning today. Many thanks.
So, thanks, Pasquale. Is there any question? Yes? Is there a microphone or something? Yes, yes. No, microphone. There is a microphone. Okay.
Oh, thanks.
Turn it on.
Thanks.
You should turn it on.
Yeah. Eccomi. If I understood correctly, you are also proposed a generative model for probabilistic model for generating graphs. And I wonder whether, do you think, is it possible to generate objects, graphs that are compliant to hard constraints. For example, they are connected, or there are some kind of properties that are to be respected. I think it is very, very interesting.
Many thanks.
Your application, because you can also generate graphs in a conditioned way by a text to graph or something like this.
Yeah.
Very, very interesting. But can you put constraints in the generation? Because I think the generation is incremental, so some kind of constraint can be inserted.
Yeah, of course. Yeah, actually, this was a problem that we deal for, in sense that we asked, can we generate, for instance, a connected graph? Okay, this looks a bit strange, but the more convenient way, because these are small graphs, usually they have 10, 20 nodes, is to generate a random candidate, then check if it is connected, and if so, include it in the sampled set. Otherwise, it is computationally more effective to discard it and to generate another step of computation. But yes, of course, I guess that it depends on the kind of constraint that you suggest. So very, very, very nice questions. Thanks.
Thank you.
Okay, thank you. Any other question? Okay, if there is not other question, let's thank
Thanks a
you
lot.
again. So, last but not least, Vittorio Bilò from the University of Salento, minimizing energy consumption by minimizing Rosenthal's potential. The ground is yours.
Yes, thank you, Michele, for the introduction. Okay, thank you. So this is joint work with Angelo Fanelli, Laurent Gourves, and Christos Tsoufis from LAMSAD, a lab at University Paris Dauphine in Paris, and Cosimo Vinci, who is also from the University of Salento, who is also here. And this is a talk based on a paper that will be presented in AMAS 25. So we belong, as Michele said in the introduction, to the work package 9.2.2, meaning that our aim is to design mechanisms for coordinating the behavior of selfish agents, uncoordinated agents, towards desirable green behavior. So we are studying a theoretical problem, but let me at the very start of this presentation convince you that this problem has important application within the topic of the work package. So let's consider this example, a very classical client-server based example. So we have a set of servers providing services to a set of clients that are electronic devices. And these devices can be connected to the servers to, let's say, wireless communication. And our aim is to satisfy the clients at minimum possible energy consumption. So since we are interested in the energy consumption, let me first give you the idea within the model of energy consumption that we can consider. So we have some basic assumption. First of all the devices, they carry the same type of request. For instance, they want to download a piece of code from the servers. And without the loss of generality, we assume that within each server, the service time is normalized to 1, just for simplicity. And this is without the loss of generality because it's not a global normalization of the time. It's a per server normalization. Okay. So as a device that is connected to a certain server S can be into one of two possible states: idle, waiting for being served, but with the active connection, or being served. So in the first case, when the device is idle, so it keeps alive a connection, but this connection does not consume too much energy. So we assume that it consumes alpha S energy per time unit. Okay? When the device is served, there is an overhead in the energy consumption. Maybe they are exchanging information with the server. So the total amount of energy consumed in this state is alpha S plus beta S. So beta S is essentially the overhead that we need to keep a more powerful communication, for instance, for exchanging data. Okay. So now, this is the energy consumption model. Now our model, the model of the problem we are interested in. We have a set of servers, M servers, and a set of devices, N devices. Every device D requires a connection to a set of servers that the number of these services are D. So maybe we need to be connected to one server only, we want to download something, but we assume that we can have a general, more complex requests in which we have to connect to a subset of more servers. And since we want to be in the as general as possible, also not any combination of servers can be feasible for a certain device. So there is a set of alternatives we can choose from. Okay, so once every device has chosen a certain strategy, a certain subset of servers, we have a certain vector of choices, sigma. And so we denote by n as sigma, this one, this thing here. Okay, I can use the mouse. Okay, and a sigma as the load of server S, so the number of clients that need to be connected to the server, and P, ds of sigma is the position that a certain device D occupies in the queue of the server of the clients, the devices that are connected to this particular server. So with this notation, the energy consumption of a certain device depends on the position it occupies in the queue. So if I'm the first device to be served, I will pay alpha S plus beta S if I'm connected to server S. If I'm the second guy, I have to first wait for the first guy to be served, alpha S, then I will pay alpha S plus beta S. So essentially, the cost is alpha S times the position that the device has in the queue plus the overhead for being served. So this is the energy consumption of a certain device. And of course, it also, you sum up over all servers the device is connected with. And the total energy consumption that we call capital C over sigma is the sum over the energy consumption of each device. And this summation can be recast in another way by exchanging the summation, the order of the summation within this formula that depends on the load of each server. This is not important to go into the technical details. The important thing is that this problem, that is an optimization problem, has interesting connection with algorithmic game theory. So if you assume that the devices are not centrally controlled, they are players, independent agents, selfish agents, and they estimate their cost, their energy consumption, their cost, according to a worst-case scenario. So they assume that they are always the last one to be in the queue, to be served. Okay, so that's to have a worst-case guarantee of the maximum energy consumption they need. So if they can be served within the battery, the availability of battery that they have, this becomes a game, a well-known game that is called as a congestion game. It's a very famous class of games in game theory. And the total energy consumption, this function capital C, has a particular and important interpretation in this realm, is called the Rosenthal's potential. And the importance of this potential, of this function, is that every local minimum, so in particular also the global minimum of this function, is a pure Nash equilibrium. So this means that if you compute the solution of minimum energy consumption, you can propose this solution to the agents and they will accept it because it's a pure Nash equilibrium. None of them can improve by unilaterally deviating from this solution. So it's an incentive compatible solution. So this is it fits the scope of our work package, designing a mechanism to incentivize the green-oriented behavior. Okay, so now, after this introduction, so our problem is to compute a solution minimizing the total energy consumption, or equivalently Rosenthal potential, within this framework. So in our investigation, we try to understand the complexity of the problem with respect to a couple of properties of the input, let's say parameters or properties of the input. The first is the value of the maximum number of servers a device must be connected to. And we call this number the size, the request size, or simply the size. So we can go from singleton connection to requiring more than just one server. And then we also study the complexity of the problem depending on whether the devices are symmetric. I mean, they are all identical or not. And of course, since we want to be as general as possible, we want to study a more theoretical problem with particular application, we try also to generalize the problem for as much as possible. So in the introduction, I gave you an example of a cost function that is affine in the position of a device in the queue. But we can consider general function, monotonically increasing function that essentially notable example can be, instead of being affine, you can be a polynomial. The function can be a polynomial. But we can also consider decreasing function. And in this case, I don't go into details, but you can consider this as a dual view of the problem. Instead of trying to optimize the energy consumption from the client side, you want to optimize the energy consumption from the server side. So to detect a subset of server or minimum energy in order to satisfy all the requests of all the clients. So this is the snapshot of the results. So we distinguish between the two cases, non-decreasing, say, increasing cost function or decreasing cost function. So for the case of non-increasing cost functions, for instance, polynomials, we have this neat separation, let's say diagonal separation between cases. So if the size is 1, example in which I, as a device, want to connect myself to a single server, downloading, for instance, a piece of code, so the problem is polynomial. The problem was already studied in a paper by Clear and Schaffer for the general case, and there is this cubic complexity in the product of the number of servers and the number of clients. So n times m to the cube. So this was known. We showed that if the game is symmetric, the complexity drops down to essentially linear in the product of number of servers and number of clients. This cubic complexity can also be reobtained if we increase the size to 2. So every client wants to be connected to at most 2 servers. It's a reduction to a matching problem. But as soon as we move from this fact, so we drop out the symmetry assumption, or we increase the number we increase the size to at least 3, the problem becomes hard. And it becomes hard even if we consider the basic starting example of affine function. We also try to consider if we can obtain approximate solution for these hard cases. And in fact, we can achieve tight approximation guarantees under the assumption that these functions are non-negative. This is essentially without loss of generality, in particular in the constant we are interested in. And the function must be semi-convex. Okay. The approximation guarantee is fairly complicated, but very interesting because it can be expressed as an infinite sum of values, and these values are connected, especially for polynomial, in particular for the case of polynomial latency function, to the Stirling numbers of the second kind. So it also has an interesting combinatorial interpretation. Then, for the other case, the case of non-increasing cost functions, the situation is completely different and more complicated. So the problem is, in general, NP-hard without the symmetric assumption, even for singletons. So even if the size is equal to 1, so it's a very bad news in this case. But if we assume that the devices are identical, we have the symmetric case, okay, we can solve the problem in polynomial time. It only depends on the number of servers times essentially the size, when the size is a constant, of course. Otherwise, there is nothing you can do. And then we also try to provide approximation guarantees for the NP-hard problems. And we could only achieve to solve the case of size equal to 1, that is already hard from the table, and we can obtain a tight approximation guarantee, which is the harmonic number h of n, so it's essentially the natural logarithm of n. So in this case, the number of clients, of devices, plays a role, while it's not the case for for the polynomial time complexity of the symmetric case which only depends on the number of servers. But we cannot go beyond the case of size equal to 1. So this is a snapshot of the results. I don't want to go into technical details. And there are a couple of interesting open problems that we could not be able to solve in our approach. So first of all, for the non-decreasing case of cost functions, for instance, polynomials, I told you that we got tight approximation guarantees, so that they cannot be improved, but the lower bounds, they hold for generic instances. So we don't know what happens if we assume that the instance is symmetric. And so size at least 3, symmetric instance, maybe the approximation guarantee can be better than the generic case. We don't know. For the non-increasing cost function, also, as I told you in the previous slide, we could only provide an approximation guarantee when the size is equal to 1. We even failed as soon as we move from 1 to size 2. So finding approximation guarantees for this case is also important. It's also open. So thank you for their attention, and I'm done with my presentation.
Thank you, Vittorio. So, any question? Any? Okay. Okay. Thank you.
So this was the last talk of this session. We continue immediately with the next one. So please welcome Giorgio Terracita, who is the chair of the next session. And also the speakers are invited to join us here. Thank you. Sta facendo lui. Ho messo tutto qua. Metti il laser. E questo lo puoi usare per fare. Va bene, per me non c'è bisogno.
Okay, thank you, Francesco. So welcome to this last session. This is mainly about work package 6. Actually, this is more application-oriented package with respect to the other work pages. The main objective here is to design and develop use cases where AI comes into action. Okay, so at the very beginning of the project, we identified mainly 3 areas, 3 domains where we wanted to apply AI, so about industry and manufacturing, distributed and smart devices, and environment, infrastructure, and networks. So during the project, we defined 4 use cases mainly. Actually, however, the work package collects also applications and applicative contributions from all the other work packages. And in fact, also these use cases are developed with the help of other colleagues in other VPs, but also other spokes. And we have a scientific partner from Università Politecnica delle Marche, and 4 industrial partners specifically working on these work package. And overall, for the whole project, we have 12 industrial cascade calls aiming to apply AI to green-aware applications. Second objective is to collect data, benchmark, testing environments, and use cases and applications all together. And overall, the project decided to leverage the SOBIC data platform. So as soon as new data sources, new experiments, new applications are defined and carried out, they are all collected in this collector. So it will be available later on. So I just conclude here my very quick introduction. We are quite late. So let's start with the first talk. The title is Artificial Intelligence Techniques and Multi-Objective Optimization in Management of Renewable Resources. Pirus Besat.
Okay, good morning, everyone. The title of our presentation is AI Techniques and Multi-Objective Optimization in Management of Renewable Resource, or research activity in the field of AI for energy storage management. Here in this slide, you can see the outline of our presentation. Considering the high cost of and also the relatively short lifetime of battery energy storage system, determining the optimal size of battery energy storage system based on system requirements is very important to increase the system reliability and also and also ensure financial viability of any renewable energy project. So we will try to developing several multi-objective optimization models to determine the optimal capacity and power rating of battery energy storage system. And also we will try to using AI techniques to predict energy production and energy consumption and as accurately as possible. And also we will try to developing an AI controller for assist the battery energy storage decision making. Here in our study, in this study, we have a microgrid system with PV panels, battery energy storage devices, and load demand, and also a connection to the external power grid. In the next few slides, I'm going to present our multi-objective optimization models. At first, the objective function. The first objective function is used to minimizing the total cost. This objective function consists several parts: total depreciation cost, total capital cost, total operation cost, total daily energy cost, total cost of the energy not supply, and also total incomes. In our model, the income is possible only when the total energy production from PV panels be greater than the total system demand. The second objective function is also used to minimize the total cost, but with considering the aging process of battery energy storage system. In fact, we will replace this objective function with the first objective function in our multi-objective model. The third objective function is used to maximize the ratio of renewable energy consumption to the total energy consumption. And also the fourth objective function is used to maximize the system reliability. According to this objective function, we have defined 6 different multi-objective optimization problems, 4 of them with 2 objective function and 2 of them with 3 objective function. About our model constraint, we have 3 general categories of constraint. Some constraint related to the power balance, some constraint related to the battery energy storage system, and also some constraint related to the photovoltaic panels in our system. Here, to respect the time, we have not mentioned the details of this constraint. And here in this slide, you can see our AI controller, some of our AI controller tasks from prediction load consumption, prediction of energy generation from PV panels, and also optimize battery energy storage operation by prediction charging and discharging process, and also the storage level in the battery energy storage system, and going to the peak shaving and load shifting in the system. I will continue with 2 computational experiments. In the first computational experiment, our goal is to demonstrate the ability of our AI controller to determine the interval for battery energy storage charging. We have 2 data sets. The first data set from our PV generation, and the second, energy consumption. Here we use XGBoost AI prediction techniques, and you can see the result of XGBoost in test data sets. And here in this slide, you can see the suggested time intervals for charging battery energy storage system. These intervals suggested when the energy consumption be to decrease, and in the same time, energy production from PV panels going to increase, and in fact, in the peak of energy consumption, energy production. Here I needed to mention that in this slide, we consider only two parameters, energy consumption and energy production, but ideally we needed to consider a lot of other parameters to determine the best intervals for charging and discharging process of battery energy storage system. The second case study or computational experiment is goals to demonstrate our multi-objective model. We have considered only a very simple model with very limited data of energy consumption and energy production from the PV panels. And here you can see the result of one of our multi-objective model. In fact, we have considered only the B-objective optimization model. The horizontal axis represents the total cost, and the vertical axis represents the ratio of renewable energy consumption. You can see with increasing the ratio of renewable energy consumption, the total cost is also going to increase in this specific day. And also we selected 3 Pareto optimal solution for more investigation. And here in this table, you can see the result of these 3 Pareto solution: B is capacity, B is power, total cost, and ratio of renewable energy consumption. For our future works, we wanted to develop a stochastic multi-objective model to deal with the uncertainty of renewable energy consumption and energy production. This model combined with AI prediction techniques, and also we have planned to develop a combination between AI techniques and discrete event system simulation when we have not enough data for training or AI techniques. Thank you for your attention.
Okay. Thank you very much. Are there any questions? Okay, I have one. So you mentioned in case 1 that you used XGBoost as an AI tool to prediction, okay? Did you explore also other methods?
Yes, we have also used the LSTM model because we have time series data, and in fact the LSTM model get better result for us, but here I only mentioned the XGBoost result prediction.
Okay, thank you. Okay, thank you again.
Thank you.
Let's move to the second speaker, AI-based surface topography optimization through sustainable laser treatment, biomedical applications. Speaker is Maria Rosaria Saffioti.
Good morning. I'm Maria Rosaria Saffioti, a research fellow here at the University of Calabria. Today I'll present you the development of our activities concerning AI-based surface topography optimization through sustainable laser treatment for biomedical application. This research is part of the AI for Sustainable Manufacturing project, for which is responsible Professor Domenico Umbrello. Here there is the outline of my speech. I will start with a brief introduction concerning the sustainable manufacturing concept, then the objectives of this research. I will show you the materials and methods employed during the experimental phase, and some results in terms of the treated surface analysis and the application of an artificial network, neural network, capable to predict the trend of some measured ruggedness parameters, and finally some conclusions and future works. Let's start by talking about sustainable manufacturing, focusing on the three pillars of sustainability that are environment, social, and economics. Here there is the definition of sustainable manufacturing as the creation of products through processes that are able to minimize the environmental impacts, conserve energy and natural resources, and also that assure the safety of everyone involved. Based on this concept, we conduct an in-depth analysis in order to select a proper sustainable manufacturing process. And among the different surface modification processes, we evaluated the mechanical treatments, the chemical treatments, the deposition methods, and the physical treatments. We classified them, and we evaluated some aspects of these processes, and we selected the one more suitable for our case. That was the laser process that is very sustainable because it is high control and precise, so it's able to minimize the material removal and so reduce waste. And although it requires an high energy, it is very quickly. And also because laser treatment does not create harmful byproducts. So also directly correlated to the process choice, there is the concept of surface integrity. That refers to the surface quality of the worked components that influence a lot the final performance of the product. And in the case of laser treatment, the surface is highly influenced by some changes in terms of metallurgical and mechanical properties. In particular, for the biomedical application is very crucial the surface state of the components. So we have the aim with this research to develop AI-driven methodologies in order to optimize the laser-treated surface for biomedical application. And first of all, we started by functionalize the surface with laser ablation. Then we analyzed the surface changes in terms of ruggedness, and then we applied our artificial neural network tool capable to predict the trend of the ruggedness parameters. All of these phases in order to reach good final performance for the biomedical components. Our starting point was this work where we functionalize the surface of titanium screws with laser ablation, and then we coated them with a biopolymer by using a 3D bioprinting. Here we start to collect a lot of data by varying the laser parameters, and so we start to analyze the influence of the parameters. Going more into detail of our experimental phase, we, for the moment, used grade 5 titanium alloy as a workpiece materials because it is the most used in the biomedical field, but we want also to investigate other materials. And for the experimental phase, we employed all these instruments. In particular, for the first phase, we used an air-cooled ytterbium fiber laser system to do the treatment. Then we analyzed the surface change by using a non-contact 3D profilometer that allows to measure all these parameters shown in the slide. And then we used the 3D bioprinter to coat the surface. Concerning the laser parameters, we conducted an in-depth analysis in order to evaluate how to vary the parameters and in order to evaluate their influence on the surface changes. And we kept constant some parameters related to the instrument, for example, the F-theta length, the focus diameter, and the wavelength. And we varied in the range shown here, the scanning speed, the power, the pulse frequency, and the pulse amplitude. Coming to the first results, here there are some different surface at varied power and scanning speed. And here we can notice that at low power and scanning speed we have an high roughness, while increasing the power and the scanning speed we have a smoother surface. And this is visible also evaluating the measured parameters. In this case, I show you just the surface mean roughness and the maximum height. And we can notice that the surface mean roughness has a more defined trend, while the maximum height has a variable evolution. And so for this reason, for this kind of parameters, we have the need to do the AI tool in order to understand the trend of the parameters by varying these parameters. Here there are other surface part of our dataset, and here are classified varying the overlap and the pulse amplitude. And also in this case we can notice that there is a more defined texture at lower overlap and pulse amplitude, while by increasing the overlap and the pulse amplitude we have a higher roughness due to the large amount of melted material that is on the surface. And here we have the same, the mean surface roughness and the maximum height for this case, where as I already know, as already said, in this case, if we do not consider the maximum overlap, the trend of these parameters is follow a not defined trend. And so we have the necessity to collect all of this data and to give them at our artificial neural network tool that was capable to measure and predict how the parameters. Here is shown the architecture of these tools, where we have 5 inputs, the 5 parameters, the laser power, scanning speed, pulse amplitude, overlap and frequency, and as an output just the mean surface roughness and the maximum height. We also considered as an hidden layer a range between 5 and 20 nodes, and we implemented a sigmoid as an activation function because it fits well our data. And we considered all in the whole data set the 90% of data for training and the 10% for testing. And from our first preliminary analysis of the results, we can observe that the mean absolute error is very low, is about the 10% for both output, although the data set is not so big. And we would like to increase the data set as in input and also with the other variables in output. And we aim to obtain a tool that is capable to suggest us as the laser parameters that we want to use to have a specific surface. And in conclusion, I will say that our research demonstrates how a simple tool can help us in manufacturing to understand how to optimize the laser parameters. And looking ahead, we want to improve our tool by increasing the experimental tests in order to expand our data set and in order to have a more accurate model. And also we did some publications submitted, and also here are listed some published and presented work, as well as the cooperation with the task 9.5.4. That's all, and thank you for your attention.
Thank you very much. Is there any question? No question. Okay, I have one. Okay, yesterday we have seen presentations from industrial partners. And I know that there is some collaboration starting,
yes.
At least. I would like to know if you already started to plan how to merge your research and the applications from the companies.
Yes, we already are in contact with the Dune company, and we are collaborating also for this project and the one regarding the milling process.
Okay, so in the end there will be an application.
Yes.
Clear application. Okay, thank you. Okay, thank you very much. Okay, the last presentation is online from Università Politecnica delle Marche. The title is A Collaborative Ecosystem for Industry 5.0. The speaker is Gianluca Bonifazzi. Yes, Gianluca,
okay.
We can see you. Share the screen.
Can you hear me?
Yes.
Okay, can I share my screen?
Sure.
Okay.
Okay, we see it. You can go.
Can you see the slides?
Yes, you can start.
Okay. Okay, perfect. So, my name is Gianluca Bonifazzi, and I'm assistant professor at Università Politecnica delle Marche, and I'm also a collaborator of Professor Domenico Ursinio, the principal investigator of this project. And this project is called A Collaborative Ecosystem for Industry 5.0, and is developed in collaboration with two companies, the Revelis and Target, but we're speaking about the companies in the future on the presentation. All the project is based on an architecture. This architecture is a collaborative ecosystem and is the foundation of the entire project and also the first deliverable of the project. And this architecture is composed by three different levels. The first level, the base level, is composed also with two different elements. One is the IoT element, and the other is the data layer element. The IoT level is composed by sensors, smart sensor, and also IoT data, and is used for gathered data from the interaction with the real world. The data layer is where the data is stored permanently and is composed by SQL and NoSQL database. This is the foundational layer because up this layer we have the second layer, and this is the business layer. This business layer is the main part of the entire architecture and is the operational and business logic of the entire project. Here we can find some different components like the machine learning component, but also the alarm system and other kind of components that recreate all the aspects of the business layer. And the last layer is the presentation layer, where we can interact with the architecture. And also, we can view all the dashboard and all the information related to the business layer. This is a picture of our result. As you can see, on the foundation of this three-layer architecture, you can find the smart sensor, the IoT sensor, all the information related to different type of gateway, the subscription gateway and the polling gateway, and all the information, the data gathered from this sensor can be stored inside the data layer, where we can find two different technology. One is the Elasticsearch database, so a NoSQL database, and the other one is the PostgreSQL database, so a SQL database. All this information can be used by the second layer, the business layer, when we can find some interesting components, like the machine learning components, where we can analyze the anomaly detection, we can do predictive maintenance, so we can analyze the smart sensor data, and so on. But we can also use the component, for example, for manage the alarm, scheduling some jobs or other kind of this type of scheduling. In the final layer, the presentation layer, we have two different technology: Grafana for recreate the dashboard and dashboarding the data, and Bootstrap to create the user interface where user can interact with architecture. But the most important component of this architecture is the mass personalization one, because the mass personalization component is the second deliverable of our project. But what is mass personalization? Mass personalization is a product strategy where the companies can combine the personalization of goods and services, or in our case, we're speaking about goods, but with the same efficiency of the large-scale production. So we can maintain the cost of the production low, but with a personalization tailored for the most customers already presented in our company, for example. But the most important things in the mass personalization is the possibility to meet the customers' individual needs, but maintaining so a low production cost. The main feature of mass personalization is 5. The first one always the scalability, because we have to produce a lot of goods for thousands or millions of individuals, always maintaining a low cost. The second one is the possibility to use data, a lot of data, and so we have the necessity to collect and analyze the data to generate a new product, always with the focus of mass personalization. The third feature is the artificial intelligence automation feature. So we need to use some artificial intelligence model to analyze and to generate the personalized content for the mass personalization. The fourth element is the dynamic iteration, because the data is continuously collected, so we need to adapt the user preference, and based on also in the feedback of the user, we can modify the product. And the last one is the manufacturer flexibility, because we needed to use a modular manufacturing to respond to answer the request of the customers, and also to answer to the supply chain request. So based on this main feature and this idea of mass personalization, we have the collaboration with the target company, a bakery based in Calabria, and with this company we speaking about the possibility to recreate and to apply the mass personalization to the product, to the goods they have produced. To start the creation of mass personalization, we have to analyze the data about the information about the company. So we have gathered two different data from the company, the orders data set and the ingredients data. Starting from this information, we have done an explorative data analysis to understand how the data is, how the data works, and to recreate in the next step the new product. So I can switch to a short live demo. We can view from this dashboarding some information related to the dataset. We use Power BI for recreate a dynamic dashboarding, so we can use, for example, filters and other kind of dynamic navigation. But as you can see from this first dashboard, we recreate a first general information dashboard. As you can see, we can have some KPIs, some minor important KPIs, for example, the number of products related to the bakery, but also the number of customers. And for each of these, we can also filter out for each client. As you can see, the client is anonymized because privacy policy, but you can also filter by product name, so you can view some different graphics related to the interest of the analysis. Another important dashboard created is related to the orders. In fact, we can analyze the order by each customer, and as you can see from the chart in the bottom right, we have a very important customer, so we need to understand why there is a bigger customer than another. But as you can see from the chart in the middle, you can see that the mean number of products for each order is not imbalanced like the number of orders itself. Also, in this chart, you can see the possibility to filter out some information. In fact, we have a range filter, so you can analyze different periods of the same data set with different also filter on customer and other kind of information related always to the orders. Another interesting dashboard is related to the ingredients. In fact, we have information about the customer, one part of the mass personalization. The second part of the mass personalization is related to the creation, to the generation of new products. So we need to know the products. In fact, we analyze the ingredients about the product of the bakery. In this case, we have analyzed all the doubt ingredients and also the topping ingredients, but we have also standardized the information, to normalize the information to 100 grams. With this information, we can analyze better the different and the percentage of each ingredient inside the various product, but we can also filter out based on different kind of product or category of product, and also filter out for different kind of product where the ingredients is composed. Another interesting dashboard created is the possibility to analyze the category of product. So we can analyze the category based on the ingredients and other kind of information, like the mean ingredients, the number of product for each ingredients. And the last one is also the possibility to analyze the price of the ingredients. In fact, as I said before, the mass personalization have the final goal to create a new product, but we maintain a low cost. So we have to analyze also the cost to recreate a new product related to the mass personalization. As you can see from this dashboarding, you can filter out based on other kind of product name, and you can see the possibility of the mean price, the minimum price, the maximum price related to different years, and also related to different customers. And very interesting information is the possibility to change the price based on the customer size. So where the customer is very big, you can lower the price to attract better the possibility of new sales. Another information always in the price is the possibility to analyze the price during the time and during the different period, so you can analyze where we can touch inflation period, like the period now, or other kind of period, and also the possibility to evaluate some discount to each customer, or some type of customer. This is a first exploratory data analysis. Based on this, we want to recreate and to create some new products generated from the main objective of the mass personalization. In conclusion, I want to speaking about the future work, because so far we have done a descriptive analysis of the data in the business context of the target bakery, but in the future we want to clusterize the customer into some groups with homogeneous needs and desires, and we want to define new product based on these groups, and also to define new product related to the needs and desire of this group created, this cluster created. For example, we can analyze the products and ingredients related most demanded by the cluster itself, and we can also recreate new product related of this information and other kind of information. So we need to move on the mass personalization to propose to the company some new product based on what we have studied in the exploratory data analysis. So I have finished my part. I leave the floor to my colleague Emanuele Storti for the last part of the presentation.
Thank you, and hi everyone. My name is Emanuele Storti. I hope you can hear my voice. And I'm now sharing the screen. Okay, so a further contribution of the project addresses work package 3, which is about smart support to task execution. And here the goal is to support more optimized and sustainable execution of the processes in the organization, enabling the assignment of tasks in a safer way from the perspective of employees. In particular, starting from an existing schedule, so an existing assignment of tasks to employees, we focus on the problem of the reassignment of such tasks under a number of constraints, which in part are dynamic, in part are static and related to the organization itself. Indeed, on the one hand, we take into account organizational constraints related to how the company operates, such as the minimum number of employees that must be assigned to a task or to a department. The skills possessed by employees, which make them eligible for assigning specific tasks, and some cost factors that I will be describing later on. On the other hand, we also take into account contextual constraints, which are dynamic in nature, that are related to the current status of the employee from both a physical and mental point of view. In particular, we aim to measure the stress level of the employee by exploiting monitoring of physical parameters such as temperature or heartbeat that can be considered as a proxy of the stress level according to a stress model, which basically maps the levels of temperature and further physical parameters to indeed a stress value. These parameters are monitored by using wearable devices under a privacy policy related basically to the need to anonymize the information. This is done by assigning smartwatches to employees and by keeping only the smartwatch ID in the system without a direct mapping to the identity of the employee wearing the device in a given moment in time. According to stress model, we are also able to take into account a predicted stress value for the future time points in order to take into account both the historical trend of the stress level of an employee and also the predicted values that all will be considered in the solution. So the approach we take to address the problem is based on mathematical programming. And the problem is modeled as a mixed integer linear programming model, where we aim basically to minimize an objective function, which is linear, by taking into account, on the one hand, the cost factors that are related to how the company manage stress values which are too high according to the internal policy. In particular, the objective function will minimize taking into account the total cost of reassignment tasks to workers by considering that workers with a high stress level will be likely to be assigned to less demanding tasks. Possibly they will be put on a break if needed, if the stress level exceeds a certain threshold. And also we try as much as possible to maintain the same assignment that we already have. This is basically done to reduce as much as possible the delays related to context switch from a task to another one, which can require moving from a location to another in the company plant. And also we take into account a number of constraints which deal with the minimal coverage for each task, so that at least we need to assign to such a task a number of employees. unique assignment such that each employee must be assigned to at most one task plus the possible break. Of course, the required skills, so each employee must possess the skills needed to execute, to perform the task. And finally, the maximum stress level, so a threshold on the expected stress level in the next future. So the problem is modeled, as I said, as a mathematical programming model. Very briefly, the idea is to have a set of workers and tasks and define a decision variable x, ij, for any possible assignment of task j to the worker I. The variable can be 1, is set to 1 if the task is assigned indeed to the worker, and 0 otherwise. The objective function to minimize, as I said, basically is the summation of all the variables multiplied by a number of cost factors related to the stress and to the overhead of the assignment. And the constraints are defined as follows. So we have a constraint for each task for the minimal coverage. So imposing that at least a number of assignments is done on such a task, and then a number of constraints for each worker in order to uniquely assign a single task to a worker according to the skills. And finally, we cannot exceed a maximum threshold for the stress level. Going to the implementation part, a prototype of the approach is implemented as a service, already integrated in the service-based architecture of the project. And we rely on IBM iLog Cplex Optimizer, which is one of the top solvers for large-scale optimization problems, including mixed integer linear programming. As can be seen from the picture, the task assignment takes into account inputs coming from other services to get, for instance, the current assignment or the current stress level of a given smartwatch ID related to a worker, or the expected and the predicted stress level in the future, but also static information like the set of tasks and the skills possessed by people associated to smartwatch IDs. I'm going to finish and briefly mention that preliminary results have been already published in a paper for a conference. Future work will include, of course, a comprehensive testing of the solution, and we'll also try further solutions, including non-exact approaches like math heuristics in order to reduce the computational time. So I'm done.
Thank you very much.
Thank you for the attention.
Questions?
Yes, just an observation. When you talked about the task allocation part and the requirements, I noted that there are some threshold of stress levels and so on regarding the different workers. But I wonder whether you considered some kind of fairness requirement. So from the point of view of every single worker, as long as you optimize the total function, but it could be that someone is more stressed and another one is less stressed. Possibly one takes all the stress compatible with of course, the threshold. So as long as you have a feasible solution from that point of view, one in principle could optimize from a kind of fairness point of view the different levels for the different workers. I don't know if I'm clear about that. Is it clear, the microphone?
The mic, open the mic, please. We are not hearing you.
Emanuele, you have the microphone switch off.
Sorry. Yeah, the audio was not perfect in iPhones. However, if I understood correctly, the question is about how to deal with the threshold related to the maximum stress level that is assigned for each worker. Definitely, this is something that is related to the particular organization. We can assign a fixed maximum level for every worker, or the value can depend on the previous stress level. So, for instance, we can weight more a particular increase in the stress level, which is quite steep, meaning that the worker in the last period is suffering a particular stress condition. So the threshold can take into account also how the stress level varies over time. But it is definitely something that we need, of course, to discuss with the companies according to what policy they prefer to choose.
Okay, thank you. I have a very, very fast last question. Do you, as a project overall, so I don't know if Domenico or Gianluca can better answer, have already plans or ongoing works to integrate your project with the industrial partners?
I'm sorry, I couldn't hear well. The audio is quite noisy.
Okay, maybe Gianluca has a line.
That's a question for me. I couldn't hear, sorry.
Okay, if you have already plans or ongoing works to integrate your project with
Giorgio, you are mute.
Ci mutano qua. Okay, please, someone can open my mic. I know we are late. Okay, let's
Giorgio,
stop.
your microphone is off.
Okay, no problem. Let's stop here. It was just a curiosity.
Okay,
Giorgio,
thank you.
your microphone is off.
Okay. Ciao. Okay, so we are stopping now our workshop.
Thank you, bye.
Let me thank you, all of you, for being here. It was a nice today's workshop, and so we can meet again in the future. We don't have now the date for the next SPOC meeting, but we know that there is this ECAI workshop in October in Bologna, and so perhaps we can also meet in some other conference in the meanwhile. Okay, so thank you again, and see you later. Bye.